wouldn't imagine a agriculture data space which is not consistent with the data space itself. Okay, so this is the resulting hourglass model that we could use we have used in SPADE. Okay, so you can see on the left you have the stakeholders, AI service providers, data users, data space governance stakeholders, data providers. Okay, this is a simplified vision, but you can recognize, let's say, roles and responsibilities that are useful. Okay, when it comes to capabilities, you have data collection and storage. So this is what the drone is doing. But you could also have specific digital twins, and we had to discuss in SPADE whether we would address this kind of digital twin. For instance, the digital twin of the drone. Okay, so yes, there are digital twins of drones, but at the end, SPADE is focusing on the thing on top. Okay, and in order to make it work properly, you have security, privacy, and digital sovereignty that you have to take into account. Once you do this, you can connect the data here and provide them to the data space. Okay, so you do it in a secure way. And on top, you can have the application digital twin, which is what SPADE focused on when we did our implementation. Okay, and once you have this, you can make available data, and data can be valorized by the users. Okay, so those are the capabilities. You see, we have to do this for end to end, and today workshop will show to you a glimpse of all those things. Okay, when it comes to standards, okay, you have a number of standards we have to follow, and but there are quite a few. So digital twin, interoperability, cybersecurity of system, drone standards, and others. Because obviously you have missed maybe a few of them. Okay, but and in the middle you have more data space. You want to follow the standards of related to the Cyber Resilience Act, the Data Act, and on top. Again, you want to follow the standards related to AI and to data, and of course using digital twin and interoperability. Okay, so the standards give us a clear and stable framework which we can use to develop our capabilities, but we also need solutions. Okay, so we've been using two open source building block. One is Basics. Okay, Basics I think we'll present later. It's for smart manufacturing, but we've been using for agriculture, which is quite interesting. Okay, and then we need to connect to the data space and we connect to EDC, the Eclipse data space component. Okay, by using this, we have an entire solution that we can present to the ecosystem stakeholders, and hopefully create an impact. Okay, so I'm done.
Thank you, Antonio.
Ice. Okay, I
Thank you,
give the
Antonio,
floor
for
to the next.
yes. We should move to the next because we are behind the schedule a little bit. I would like to share your screen, Nancy, please.
Hopefully you can see everything clearly. All right, so I'm Anssi Rauhala from University of Oulu in Finland, and I'm going to talk about the national differences in the implementation of the drone regulations in EU. So, a little bit of background. In 2018, we got the new rules on common rules in the field of civil aviation, and these new rules apply to all unmanned aircraft system with very few exceptions. And these new rules replace the old system of a mixed set of national rules and the EU level rules that only apply to very heavy UAS. And this new regulation also further mandated EU Commission to regulate the UAS sector, and it gave EASA soft powers to introduce guidance material standards and coordinate the actions of the member states. So with this new rule, we got the EU Commission implemented these regulation 947 and 945, and these gave detailed provisions okay, for operation of UAS, and gave requirements for the design and types of UAS and rules for third country operators, etc. And we got this risk-based approach that categorizes operation to open, specific, and certified categories. And with the new regulation, we got mandatory UAS operator registration and pilot training for most types of UAS. And these are even for the recreational use in the lowest risk open category. But the implementation of these rules and procedures are up to the member state and their competent authorities. So in SPADE project, we have reviewed the regulations at European and national levels and further evaluated the national differences in implementation of these new rules and what are the differences in the public services available. And we placed focus on open category operations as these information about these is most easily accessible. And we analyzed these differences by comparing the relevant sections of the website provided the competent authorities of each EASA member state. So first of all, about the language. So as you can see here in the map, only very few of the member states provide all the information in English. And of the member state that provide at least some information, there's a wide variety what kind of information is provided. Typically, you might have the registration procedure available in English, but that is not always the case. And it's very typical to have the map service, aviation map service available in English. But for example, the training materials are not so commonly available in English. And this lack of English information is obviously might be a problem for like a third country operators, which according to these rules must register in the first member state that in which they conduct operations. Might also be problem for like immigrant labor working in the field of UAS. So then to the training materials. As you can see, less than half of the member state provide open access to the training materials. And it's more common to only have the training materials available after you register to make the operator registration or register to the website. And this is also issue with regards to good governance and open government data. And also migrant workers, third country operators might have issues if you need a local electronic ID to register to the website. And also EASA warns against a fraudulent website that offer non-official pilot licenses for a price. So I don't think it would be very surprising that people, when they cannot get the training materials openly available on the country they try to operate, they might look for additional websites and find some of these fraudulent websites. So then the new rules set some rules regarding mandatory reporting of some incidents and occurrences. And roughly 2/3 of the member state provide information on the mandatory incident and occurrence reporting. But of these member states that provide the information, only roughly half give specific guidelines for UAS on which type of incidents or occurrences must be reported. And if the users, operators, pilots are not informed about what they must report, it's very difficult to then proactively analyze safety risks if a lot of these incidents are not reported. So then for insurance, so the new rules mandate insurance for all UAS that have takeoff mass over 20 kilos. So as you can see, some countries have opted to only have the EASA mandated rule for UAS over 20 kilos, but many countries have set rules for even lighter UAS, and some countries require this insurance for all UAS. And this highlights the potential risk of regulatory fragmentation, as many of these sectors that are related to UAS operations fall within the regulatory powers of the member state and not on the EU Commission and the EASA rules. So then we also looked at some countries, 3 countries from each: Central and Eastern Europe, Northern Europe, Southern Europe, and Western Europe, and took a bit more deeper dive into how they have set up their systems. So first of all, we look at the costs. In what kind of services do you need to pay for something? So as you can see, quite a few countries requires some cost when you do the operator registration, but many of the countries after that provide the training and at least for the open category A1, A3, the examination for free. But some countries, for example, Greece, Netherlands, have opted more for outsourcing the training. So it might be case specific that do you need to pay separately for everything, or is it all included in your training material package? But even in the countries that provide training and A1, A3 exam freely, typically the A2 exam involves some costs, as this should be taken under supervision. It shouldn't be available in online. So then to the ease of access and openness of services. So in most nations, you can register by electronic ID, Germany being the one exception. And usually there is like aviation map service that is openly available. Only in Italy it seemed that you need to actually subscribe to that service. But one issue is that the new rules give the member state ability to set up permissive UAS zones where you may be exempt from one or more of the open category requirements. And it seems that fewer of the countries have opted to even inform users about possibility for this. So seems that some of the member states have opted to more permissive approach and some like more restrictive. And then some anecdotes from different countries, how they have set up their system in a different way. For example, in Hungary, all the operation over inhabited areas require temporary designed airspace, and you also need to register your UAS in addition to the operator registration. And in Poland, each flight should be conducted only after informing the Polish Air Navigation Services Agency about the intention of the flight. In Norway, non-citizens must notify the authorities if they are flying with an UAS containing any sensors, including camera. And in Germany, which is a federal state, the federated state authorities may authorize some deviations from specific operation conditions. And there are much more of these anecdotes where different member states have opted for different kind of approach. So in conclusion, there's a clear variety in the implementation of the regulations and variety in the available services. And member states adopt these new rules at different non-synchronized pace. And even though the actual EASA regulations are harmonized, but the implementation of these regulations in the member states seems to be pretty fragmented. And on top of that, the member state enact additional rule for this EASA regulation framework. And also, like was the case with insurance, there are many UAS-related sectors that fall within the regulatory powers of the member states. And these all consider the open category rules, but there is even more variability accepted for the specific categories, since these rules give a lot of freedom to the member state, for example, in what are the accepted means of compliance with the requirements. So that's all for me. So
thank you, Anssi.
I give the floor to the next.
So, good morning, everyone. We are two presenters from the Norwegian University of Science and Technology. My name is Vilma Zubinaite, and together with Ken Hellerud, I will present our work on the social and environmental aspects of drones in forestry. We focus on two connected questions. First, the environmental impact on the wildlife, and second, the social dimension with a focus on gender participation. Even though there are more than 1,500 studies on drones and wildlife, we still cannot reliably predict how specific flight settings affect animals. In practice, drone missions are usually planned to optimize battery life and area coverage, but ecological safety is not really included. At the same time, regulations are quite general. They rely on fixed no-fly zones or standard altitude limits that do not account for differences between species or environments. So there is a clear gap between how drones are used and how their impact is understood. To address this gap, we developed a framework based on a systematic review of 39 studies. This framework has 3 components. First, factors. These are what we can control, such as altitude, flight path, noise, and flight frequency. The second one, responses. This is what animals show. For example, moving away or reacting to the drone. But there is the key point. Behavior alone is not enough. And animals can be stressed even if we don't see anything. And the third component, sequences. These are the long-term effects, such as habitat abandonment, reducing breeding success, and even population-level impacts. So what looks like a small disturbance can become a much bigger problem over time. So what do we do with this? We move from theory to practice. We develop a simulation approach using an acoustic environment based on Unreal Engine 5 and validated sound propagation models. This allows us to simulate how drone noise spreads in a real environment. And we can place virtual listeners, for example, at nests or burrows, to estimate what animals actually experience. This simulation, this allows us to test emissions before flying. These simulations gives full control over flight parameters, including drone type, altitude, flight path, and environment. It is also validated with real-world measurements, so the results are reliable. This means we can evaluate drone missions in advance and immediately see their potential impact. So what does mean in practice? First, we move away from general rules. Second, we test missions before flying and adjust parameters if needed. And third, we include ecological impact in planning. So overall, we move from precaution-based rules to predictive wildlife-aware planning. So far, we have focused on environmental impacts. Now I will briefly move to social dimension of drone technology adoptions. The key question here is simple: who is actually using this technology? Because technology does not affect everyone equally, it often reflects existing inequalities. To study this, we use multiple data sources. This includes surveys and project participation records, as well as interviews with experts and local communities. This helps us to understand the real challenges people face in practice. We also compare the results across different countries, including Spain, Norway, and Greece. So this allows us to identify patterns from different perspectives. And the results show clear differences between sectors. In agriculture, there is a moderate gender balance. Women are often in leadership or advisory roles, while men dominate technical drone operations. In forestry, especially in Norway, the gender balance is low. Men dominate both operational and technical roles. In livestock, the imbalance is even stronger, with very low participation of women. So overall, we see a clear pattern. Women are present, but mostly outside technical roles. Men dominate, especially operational work. And this leads to an important insight. The barriers are mainly structural. They include institutional factors, culture and social norms, digital literacy gaps, and regulatory complexity. Interesting fact is that technical ability is not the main issue. So this is not about ability, but about access, opportunity, and context. So what helps? Flexible trainings, mentorship, and better visibility of women in the field. Also training that is inclusive and adapted to real life situations. So the key point is we are not trying to change individuals, but to change the system around them. And to conclude, achieving inclusive drone adoptions requires more than simply increasing participation. It requires structural changes. We need better outreach, more flexible learning opportunities, and more inclusive design of training and tools. So the key message of this presentation is both environmental and social aspects must be considered together for responsible drone use. Thank you.
Can you see my screen?
Yes.
Perfectly, thank you. So I will give a short overview over our work about acoustic sensors on drones. But maybe the first question is, well, power. But the first question, why should we even consider using acoustic sensing on drones? Well, the main point is that cameras are quite often limited in a daily situation, like fog or dust or even darkness. If you want to detect some events, for example, then an acoustic sensor might be the solution, since the camera is not able to detect these things or these objects you want to detect. Additionally, many relevant events are audible, like machinery or some kind of vibration you can have from your machinery, but also when we consider wildlife or animal activity in general, they also most of the time make very distinct noises, so that we can use these signals to detect if the health conditions of the animal is okay, or maybe we have to take some countermeasures to improve it. So as you can see, it's very clear why UAVs can use acoustic sensing to enable large area monitoring beyond line of sight. In SPADE so far, there is an existing work of colleagues of mine who are using cameras, for example, to detect sheep. But also in this case, there are limitations, like it depends on the light, it depends on the line of sight, and also the ground sampling distance. Also, as I already mentioned, the acoustic sensing can be a complementary modality, means we can enable a robust detection of objects, machines, and whatever beyond visual occlusions and low light situation, and be able to then enrich and cross-check, for example, visual analytics. What did we do in specific? First, let's take a look on the state of the art. There are already kind of investigations out there of different research organizations and research teams working on these issues, trying to make use out of a UAV-borne acoustic sensing, but they usually use small microphone airways which are mounted near the drone platform itself. But as you can imagine, a drone is a quite loud device at the end. So strong constraints are in the high rotor and airflow noise, induced noise by wind and vibration. And at the end, this make the integration and placement quite difficult. So there are different approaches that they use airways which are mounted on the frame or even outrigger airways. So you can you have to imagine it in a way that you have some kind of arms about 50 centimeters to 1 meter, so that you increase the distance of the microphone to the drone. Here on the right side, you can see one of our measurements we did in our measurement room at the Fraunhofer IDMT. Here is the drone mounted in the center of this polar diagram, and the blue lines show the sound radiation. And within this green square, you can clearly see that under or beneath the drone, the influence by the rotor airflow and so on is the highest. And it also depends on the distance. So the blue line is about 1 meter away, whereby the red dot here is, for example, 10 centimeters below the drone. So this was also our approach to say, okay, we want to develop a framework which can be mounted directly on the drone so that we can use the drone itself as kind of a windshield. And as I already mentioned, the noise introduced by the operation of the drone, no matter if it's the wind noise or the motor noises itself, are quite a challenge. So there are different ways how to deal with this kind of noise. There, on the one hand, there are the classical post-processing approaches, like, for example, spectral filtering or source separation. But lately, there are also developments regarding AI-based approaches, like data-driven denoising or even localization models. The big benefit, of course, is and that it shows potential for improved performance, but at the end, it's always this compromise between a robust and efficient versus a promising and expensive approach. So there are some key research gaps, especially for agriculture. Namely, most of the work we see in acoustic sensing is done so far for speech or gunshot sounds. So usually very loud and very distinct noises, but not for broadband agricultural sound scenarios where you have to cover from animals to heavy machines. So that means we have a lack of domain-specific data sets, as I mentioned, livestock, insects, machinery, and this also leads to a little evaluation under realistic ego noise of the drone itself and also low signal-to-noise ratio conditions, especially if you're talking about very silent noises like an insect, for example. So what we did at Fraunhofer IDMT, we were developing a modular acoustic front end, which enables different modular microphone configurations, which are directly attached to the UAV. Our microphones are integrated in a way that the position can be changed easily within an aerodynamic housing, which helps us to reduce aeroacoustical influences caused by the rotor induced airflow, and also enables us to have an embedded processing unit so that we can process our audio signals already in real time directly on the drone itself without the need to first transmit the signal to some centralized server infrastructure or something. As I also already said, it's designed to be able to configure in different ways. So our framework and our hardware sensor is able to switch the different microphone airway positions, so it can be easily adjusted to different use cases. And the main point during this developing process for us was really to focus on the compatibility with existing UAV platforms. So our goal was that it can be used on any drone which fulfills the requirement in payload, of course, but it does not need to be a specific drone the operators at the end need to buy. So here on the right side, you can see a simplified diagram how it works. So we record our raw multi-channel audio directly on the drone. We have different parameters we can configure in the pipeline. For example, how the microphones are processed, which kind of beamforming algorithms are used, and what kind of denoising is used, and also, as I said, the microphone positions. And through this modular approach, we are able to extract or record acoustic features for different applications. Our evaluation was done with some generated data sets. Here on the right side, you can see a picture of our measurement room, a loudspeaker, and here a symbol of a drone, which shows how we created the data sets. We used animal noises and other agriculture-based noises from the open source FSD 50K and ESC 50 data sets to generate our data sets. Here you can see a list of the different sound categories we introduced there. And this allowed us to generate realistic data set, how it would be in real life. And this we then used to measure how well our noise reduction is working, how well the preservation of the signal characteristic is working, and to make sure that not a single metric at the end is overpowering. We also introduced a combined quality score adjusted to the needs in agricultural settings. The conclusion, we presented a modular acoustic front-end system, which is adjusted for a broadband agricultural monitoring purposes with this flexible sensor layout and the processing pipeline. It specifically targets the needs of the agricultural use cases. So we are able to bridge the gap between generic approaches in UAV acoustic sensing and also the domain-specific signal characteristics which are occurring in the use cases SPADE is focusing on. But of course, also there will be future research needed to even improve this approach. Means, for example, extending in even more hardware configurations and maybe even more powerful approaches, which are then, of course, will need higher computational power, which we decided not to focus on, because, as I said, we really wanted to process everything on the drone itself, so that there is no transmission or anything needed of the raw signals. With that, at the end, thank you for.
Clearly.
I forgot to unmute. I'll do my presentation shortly so we can try to keep the time. As Iris said, I'm research engineer at University of Southern Denmark. I'll present the physical part of the SPADE. So the work package that we have is basically a supporting work package to most of the other work packages because they need physical systems to deploy these systems on. And we were given the task, or we defined the task, that we wanted to reuse some of these components across the different use cases. So just as Kevin said, you want to make something that can be scaled to any different system, any different drone. We did the same because we had to accommodate a wide range of different drones that I'll be showing you today. So first off, how do you actually start with this given task? We defined a range of components you could, or the partners could choose from. So we both comply with a top-down approach or a bottom-up approach or an iterative workflow. So in case you want to change the compute board, we can easily do that. In case you want specific sensors, we can easily fit those sensors on the specific airframe. Regarding the airframe, we also need different airframes to actually accommodate these different sensors and these different systems. Sometimes you need to carry a small light camera, other times you need to carry a heavy planer that I'll also be showing you. So we created a wide range of drones, and we are mostly using off-the-board components. We realized that the larger the drone you make, the more often you need to build the drone around the tool and not build the tool around the drone or build the sensor onto the drone itself. So I'll also be going slightly into detail with that. So first off, here are two small examples of the small QAV250s with, on the left side, a LiDAR for forestry scanning or any type of scanning in any environment. This is specifically designed for below canopy scanning. So that's why the radar or the LiDAR is on top and not on the bottom as you usually see, because we want to go below canopy. On the right side is a soft-mounted camera, 16 megapixel, with the drone that can do livestock monitoring or taking pictures of crops or anything really needed. First off, this is a very iterative process, so we did learn a lot through this process, and some of the components we chose actually broke under shipment. So we had drones shipped to different partners that were returned because they simply couldn't take off, and they were able to take off right when we shipped them. So it's a very iterative process, and we went through these problems with the partners themselves. Next off, this is another example where we made a very simple drone. The camera didn't show up in time, so we had to strap on a USB camera. But we could test everything, and we could actually send the drone with this camera, and then they could actually put on the specific camera that they needed. Then for the acoustic sensor, again, this is a slightly bigger drone that could carry this acoustic sensor from Fraunhofer. And this is also the specific drone that they used for the acoustic fingerprint or processing, or the acoustic analysis of this drone. We also participated in Shift Happens as a challenge provider, which Shift Happens, for those who don't know, is a student challenge in Coimbra, Portugal, where students could actually compete and learn a lot about the SPADE, learn a lot about how can drones be used in different environments, how can drones be used in forestry, open field projects, and livestock trials. And we wanted these students to learn and actually teach them, how do you develop for drones? What are some of the thought processes you need to understand, and some of the thought processes you need to start wrapping your head around. So we gave them the task to fly autonomously in an ungiven environment, where they should then map the volume. And this was, of course, inspired by the open call below canopy flying. We got the two winners of the teams, and they were very happy. And one of the teams came all the way from Turkey. So it's a very nice thing to be able to inspire these young students to work with drones themselves. Of course, we make an iterative process, and a part of SPADE is to have these drones being flown in swarms. So I rebuilt the Shift Happens drone and made some small updates based on the feedback and what I learned in that challenge. So now I updated some of the components and made them more easily to scale and manufacture multiple of these drones. And we shipped those off to forest mapping open call we actually shipped Stefan took them with him to Norway, and then he shipped them off. And the same goes for the camera drone. This is now in Mallorca with Pierre, that you will also be hearing a talk from later. So now, in the beginning, I also mentioned that we wanted to do tree planting. So this was the point where I joined SPADE, and some of my earlier colleagues made an attempt to actually make a drone that could carry this planter that is being developed by Nebio in Norway. It was based on a Tarot X4 frame, and it was marginally be able to accomplish the task, but it wasn't to a satisfying rate. So we did a lot of upgrades. I fully restructured the entire frame and the sensor. The center mounted plates were manufactured in Norway as well. And that allowed us to actually build a drone that could plant trees. And this is the first tree planted drone, or tree planted seedling, drone planted seedling, to our knowledge. And you can see how easily the drone lands and takes off, but there are also some obvious flaws in this design, specifically the landing legs and the weight of the system. So we were constrained to how strong we could make the planter. So this all accumulated into an IEEE Transaction on Mechatronics article. Feel free to read it. I highly recommend it. It's a great work from colleague Stefan from Nebio. Then we have the Sky Planner 2. As I said, we were restricted by the weight a lot. So I reduced the center mounting plates with almost half the weight. And that alone saved us the drone structure itself saved us 3 kilos of structural weight. And it's a lot stronger now with legs that is also in an open call for self-leveling legs. We had some specific requirements for the motors themselves, and these specific requirements have been accomplished by using a small CMOD S7 FPGA, and I can say that that the task is a true minimal delay FPGA PVM mode conversation implemented on the drone. So very low power, very low latency. We also developed a ground control station, and the files for this and the build process should also be coming online soon. It's a desktop setup that you basically carry in a suitcase, and then you can use this setup to configure your drones in the field. And we use it specifically for testing because this is a lot easier than doing the testing indoors in some scenarios. Thanks a lot. Feel free to look at any of our publications or some of the other research we have going on focused on high voltage drones. Otherwise, I'm giving the floor back to Aris.
Yeah, so I'm Steve Brewer from the University of Lincoln. We're working on the trustworthiness platform, which brings together many of the ideas that you've heard about so far, together with the things we're going to be hearing about in terms of the technical platform. So the idea here is to develop a framework, which is a collection of collaboration agreements and mechanisms to enable the various components of the system to work together to foster this climate of collaboration. This involves building on the things you've heard about in terms of the standards and the interoperability factors to log the risks and ensure that systems and processes meet the trustworthiness standards which are emerging, which we heard about earlier from Antonio. What we're doing is analysing the work across the project, the different areas, collating the key elements needed. This will all be presented in a report which will be published on the SPADE data trustworthiness framework scheme, which will sort of help bring the elements of the project and the various partners in the project together. This helps additionally in terms of the sort of go-to-market strategy of what's been achieved in the project in terms of membership agreements and what the roles and responsibilities would be once these different components of the system are working together. So we're working with, as well as the University of Lincoln, Angela McMillan, who's a lawyer, subcontractor with specialist area in digital and data collaboration, and what the structure of these kind of legal agreements that will be needed in full implementations of the SPADE technology going forwards. As I mentioned, we're working with Trilog on the kind of standards as these are emerging. I'm also have some involvement in some security standards because this is a very novel and new growing area where the teams developing the standards are very interested in the kind of work that SPADE's doing in terms of prototyping new technology and these sort of challenging areas. This was some of the early work we did in terms of what a digital data marketplace would look like. So what happens when you start to integrate the different drone solutions is that there's a need to share and exchange data. You've seen from the other talks, got things like the civil aviation groups, the environmental factors, all of these need to be incorporated. We were looking at a governance model which is very inclusive, so that the various stakeholders, participants in any solution, all involved in that governance and ensuring that the standards, the security is upheld, but also the ability to share and exchange the data is maximized with things like AI services that are needed for these schemes to flourish. So we're looking at sort of the kind of membership organization structure and services and how to develop a kind of marketplace with the data that's needed and produced by the different scenarios that we're looking at. So really finally, we're going to be summing all this up in public-facing report on the trustworthiness framework by the end of the project, the next few months. This blueprint will help with future implementations of the SPADE platform and the different technologies in terms of governance, membership models, and forums for exchanging the data. We're basing this on the pilots, which you've been hearing about, the case studies and other sister projects. And then we looked at looking forward that this blueprint will provide guidelines for digital transformation strategy for other similar sort of communities and scenarios in the future. So thanks very much for your time. There's contact details if needed, and I'll hand you back to Aris.
Well, I'm going to talk about the digital twin platform that we developed during the SPADE project. And well, I'm Pablo Couñago. I'm a senior engineer at Gradient, and I'm part of the Intelligent Systems department. And my work focuses primarily on Industry 4.0 technologies with particular emphasis on digital twins for factories and production lines and so on. And I would also like to acknowledge my colleague Pablo Mejuto, who is the project manager for SPADE from Gradient side. And well, as I said, I work in industry. I use industry standards. So one of the main actors in the creation of digital twins in the industry is the asset administration shell. So the question is, what is an asset administration shell? Well, it's an Industry 4.0 standard, and it's designed to provide a complete representation of a physical asset. You can think of this standard as an interface that connects the physical world with its digital counterpart, and it creates a common communication channel with a common language, and so these two sides can talk to each other seamlessly. What makes the asset administration shell powerful is that it provides a standard data model with a defined structure and a consistent API. And thanks to that, digital twins from different manufacturers or different companies can interoperate easily and without friction. The asset administration shell is organized as a hierarchical model, like it's a tree-like structure made of different layers. And at the core of this structure are the submodels, which are groups of properties of the same category that organize the relevant information and the functionalities associated with a specific asset. Each submodel focuses on a particular aspect, and for example, we have the digital nameplate, which includes basic identification details of the asset. There's also the technical data submodel, which describes how the asset is built, how it should be operated. And we can also include many more submodels like contact information or operational data with real-time information of the asset and so on. There's also a submodel that can integrate AI algorithms or other external tools with a digital twin. So it's quite complete, and it's growing with new submodels right now. So as I said, this asset administration shell standard is used in the industry. So the question is, can this standard be used outside of the industry and be used in the agricultural sector? And we think it is possible, and it fits quite well the use case we're presenting. So we think the digitalization is at the core of Industry 4.0, and the idea of modeling processes and data structures and so on is not limited to manufacturing. The same principles like structuring the information and standardizing the interfaces is just as useful in other sectors like healthcare, agriculture, energy, transport, and so on. So we think that anywhere you have assets, data, and processes, the asset administration shell can bring value. some of the key features that make the asset administration cell interesting is that the use of standard data structures give a consistent way to describe any type of asset. The use of standard interfaces enable interoperability between systems. As I said, different vendors can produce different digital twins, and they can interoperate easily if they follow the standard. There is also the benefit of the reusability of some models. They are standardized. They can be reused from different from use case to use case. So you don't have to develop your own data structure from scratch. You have some ground to start from, and there's also a wide range of protocols, communication protocols, and data sources that are also integrated into the platform that are mapped into the data structures created by the standard. So what is the tool that we use to create a digital twin based on the asset administration shell? Well, the most advanced tool in this field is Eclipse Basics. It's an open source middleware that provides all the building blocks necessary to create digital twins following this EASA specification. It is the most complete and up-to-date implementation of this standard to the date. And it's built on a scalable microservices architecture, so it can be it can fit from a very small use case with a few assets to a very large production facility with hundreds of assets. So it's based on microservices. So if you need more assets, you can simply deploy more instances in your cloud infrastructure, and that's it. Basics is also very good and interoperability. It provides tools for the integration of different data sources like industrial protocols like OPC UA or many more, but also more generic protocols like MQTT or REST APIs, or even integrations with databases. If there's any data source you have that it's not already provided in the framework, you can add it quite easily. And finally, Basics is backed by a strong institutional support from organizations like Eclipse and the Fraunhofer. So it's a long-term development, and it's quite stable and quite complete. Then the first step we have to take to create a digital twin for SPADE is to create a data model. In this case, the common factor, the common ground of SPADE is the use of drones. So we had to create a data model that can capture the key properties of off-the-shelf drones. So we made a bit of a study, and we selected some of the key properties that all drones share in common, and we created a data model that can capture all this information in an organized way. So to keep everything organized, we group these properties into category-based submodels. So it's quite clear and quite easy and consistent to manage the information. Some of the important characteristics of this model we created are, first of all, the data model we created acts as a template. So it's an empty structure that can be tuned to the specific use case. You can remove properties or remove some models that are not needed. And this template serves as a base to create a digital twin. It's reusable, so it can be used in many different instances. And so it's quite important, this concept of the template. The EAS itself is an empty shell. It's just the data structure. So it has to be deployed into a real world digital twin, into a set of microservices that deploy this instance, and then it has to be fed with information from the real world, from data sources you may have, telemetry or whatever you have for your real world asset. And once the digital twin is created, it exposes a standard REST API that mirrors the structure of the information defined in this template, in this model. So it makes it very easy for external services or applications to integrate with a digital twin, because these REST APIs are known and standard, and you know how to make a request and what are you gonna receive in response. So the digital twin platform we created is quite flexible. We based our work in the framework of Eclipse Basics. It is we deployed all the digital twins in a Kubernetes cluster, and around this framework, we created a set of tools that allow us to streamline the process of creation and management of digital twins, from defining the AAS model to generate a digital twin from the template, to deploy it to the cluster, and manage all the life cycle of the digital twin with minimal effort. For this, we created a set of services around the basics framework. And first of all, we created this template manager. Template manager is a tool we use to handle these templates. As I said, we created a template for drones because it's the common factor of SPADE, but the platform is able to handle many more templates from other assets that may be needed in the future. So it's expandable, and it's quite flexible in this sense. This template manager relies on an object storage, MinIO in this case, where we store all the templates in an AASX file format, so it's compatible with the Asset Administration Shell standard. And there is, on top of this, there is an API that allows external services or external users to interact with this service to create more templates, to list the available templates, or update any template that is already created. Then there is the Digital Twin Manager. This components takes a predefined template selected by the user and uses it to create a customized digital twin for a specific asset, removing unnecessary properties or whole sub-borders if they are not necessary. The resulting AASX file is also saved back to the object storage to allow for versioning and version control. As the template manager, this service also exposes a REST API that allows external users to manage digital twins, to create new ones, or delete an existing digital twin, or whatever may be needed. Then the next component we created
Pablo,
is
just to inform you, we already passed your time. Please conclude as soon as possible, because we need to move to the next. Sorry.
So the next part is the digital twin deployment API, which is a wrapper around the Kubernetes functions. So this service creates the real digital twin in the infrastructure. It takes the template created, it generates configuration files and deploys all the microservices required to have the instance running in the cluster. And then we have this web interface, which is provided by Basics. It's a basic interface to show the structure of the properties in the data model. And just to mention that all the software created in this project from our part is is provided as open source in this repository. You can have you can check it. And I think that's it from my part. Here is our contact information in case you have any questions, and thank you for your time.
Okay. So my name is Jorge Almela Miralles. I'm here on behalf of Bavenir, and we are responsible for the side of interoperability between the pilots in SPADE, what we call the external interfaces. Today I'm going to be brief, but I just want to go over the fundamentals of what we are doing, and then to provide an example of what we are doing in SPADE. So basically, what we are doing is to enable the different pilots to be able to share data or assets or services between them. And so, for instance, they could access remotely the APIs offered by, now just presented by Gradient, digital twin, and remotely create a digital twin and share data there that will then be displayed in the digital twin, as an example. So what are the building blocks to make this possible? So we start from raw data that it's heterogeneous in nature. And the idea is to align it to well-known standards, define interfaces for the APIs and the data itself, and then assign them unified and unique identifiers, and then making them available over APIs. So from having raw data stored somewhere to make this data discoverable and exposed over APIs that are secured for the members of SPADE or authorized users. Then we have isolated silos at the beginning, which could be the different pilots in our case. So what we want to do is to make those silos discoverable in the vicinity for authorized users, and that they can expose the things, assets, data that they want to share in so-called catalogs or marketplaces. So then this data, once it's discovered, can be accessed by remote users. In order to work, we need trust and to bring some value to the ecosystem. So therefore, we need a framework to secure the interactions. In the case of SPADE, we have a flexible mechanisms to organize the different users or stakeholders into organizations and to create partnerships between them. Then they can define so-called rules of engagement in contracts that are following ODL standard, and where they can define access permissions and for what purpose they want to share some asset, either data or a service. Then this facilitates the reuse of data. For instance, once the service from Gradient, for instance, to create digital twins is exposed within the SPADE network, different users can integrate with it in the same way, without the need of interaction from Gradient in this case. So first, we want to create communities that can join within partnerships and exchange contracts among them. They will decide who can access their data, and finally they will define the conditions on which this data can be used, and of course terminate contracts if needed. So what is the concept in SPADE? We are connecting the different different pilots with the digital twin platform. Each of them share a data broker or SPADE node that can discover each other and exchange configuration data for instance, for establishing those contracts, or can discover each other and each other's assets. Each of these nodes is hosted by the owner, so those are remote locations. And finally, the platform, of course, has to offer identity management means. So each of the sites has its own certificates, for instance, for signing interactions. Users have their identities, and each asset has its own identity. as an example, so for SPADE, we have already the platform running that is accessible. And there you can see for each of the users, you can discover which are their active nodes. And within each of these nodes, we have a interface such as this one, where they can see their items, they can see the adapters that they use to integrate their items, they can sign contracts, and then they can do a discovery what else is available. So for instance, here we have example of the service for creating digital twins. Here, thanks to also the interoperability features from the basics framework, we can map then the metadata description from our platform with theirs. And whenever you create a digital twin, then the data can be connected almost seamlessly once it's available here within the platform. So here you can see some of the functionalities, like how can you establish contracts. You can see the properties exposed by each of the services. In this case, just creating a new digital twin for which then you will get an ID and some instructions on how to interact with it. And on the left column, you can see some other assets that are shared. There is just an example of how to create a contract. So we based, as I mentioned, on the our policies on the ODRL standard, and we just simplified it by selecting a subset of the rules available and allowing users to create within the user interface those contracts. So in this case, we just tested the read, write, and then subscribing to events or services. And once this contract is approved by both parties, then this data exchange can go forward. So within this platform, the idea is to enable interoperability between the partners so they can, within the same platform, exchange their services and data. And then there is a secure way how to foster this collaboration within the project. Okay, try to be very fast to keep the time. So I'm happy to answer questions or via mail. Thank you very much.
So so I'm Pierrick Leguillou from Any Solution, and I am the coordinator of the open field agriculture pilot of SPADE project. So just to give you a bit of context, the pilot is undertaken in the island of Majorca, and we have two different use cases. As you can see on this map, it's on two very different terrain configuration. One is on the mountain region of Majorca on traditional terrace crops, where you can mostly find fruit trees, and mostly olive trees and citric trees like oranges and lemons. The second use case, it's on potato crops. So here you have the traditional monoculture crops on a fairly flat terrain. So these two use cases are, you can see, very different, and it was very interesting to see the differences in when you use and you apply drone technology in this type of crops. So in this pilot, what we wanted to do was first to see how this drone technology could support traditional farming, especially in the monitoring and management of their cultures. And we had in mind, mostly three different types of application. One was the detection of plagues and disease. The second one was health monitoring of the different crops. And the last one was spraying application. Spoiler alert, the spraying application was not as successful as expected, but I will come back to that later. As secondary objective for this pilot, what we wanted to do was to raise awareness about the technology to farmers and to the sector, because in the Balearic Island, and I think in most European region, the application of drones in agriculture still is very seldom. And in the concrete case of the Balearic Island, when we started the project nearly 3 years ago, absolutely no one was using drone in agriculture. So at the same time, what we wanted to do in order to facilitate a bit the work for the farmers, for the uptake of the technology, we have done some tests and research on the cost efficiency of the technologies and to assess the needs and barriers of the farmers. So to do the first objective of monitoring a bit the health and how drones could support the management of the cultures of the farmers, we have been using mostly drones equipped with multispectral cameras. You have an example on the right of the screen where you can see one of the results that you can obtain. These are index maps where you can easily interpret where a crop is performing well or not. So what we've seen is that in flat monoculture crops like potato crops, it's quite easy for farmers or for an agronomist to generate the maps, but also to understand and interpret the map, which is very important. On the contrary, when you look at terrain like mountain region, which have very high, very pronunciated slopes, it's quite hard to interpret, especially with fruits, because the growth is very different. In this specific example, you can see that you have a lot of mixed trees. It's not monoculture, so you have mixed trees, and it makes it quite difficult for the farmers to interpret. So we've seen that in such use case, farmers need to have like technical support or support from someone who could analyze and who could help them to interpret the results. One of the second objectives of the pilot, as mentioned, was to work on disease detection. And in this case, we focused on two specific diseases. One is the olive leaf spot disease, and the second one is a fungus called Alternaria on the potato use case. For both use cases, these diseases are very relevant for the Balearic Island because they represent up to 50% loss of production in those crops. So it was very important for them to be able to better identify this disease. How we've done that? So we've been gathering data. We've been doing performing some flight mission. We're working with the two local partners that we have in the project, which were the agricultural cooperatives of Sawyer and another farmers cooperative called Mallorca New Potatoes. And so with them, we've done this flight mission where we've put ground markers indicating exactly where infected trees or plants were and where the healthy one. These data have been provided to one of the winner of the beneficiaries of the open call that we had in the SPADE project. And I will not talk a lot about that because I know that later on there will be another session from our colleagues from the winners of the open call from STAM that will present the results of their tool. But just as you can see on the map on the right side, bottom right of the screen, what you obtain is a tool that gives you a map with some percentage of estimation of potential outbreak. So this helps farmers to identify where they can have some infection of their crops. Another work that we've done on through the pilot, it was also a test because a lot of farmers were telling us, okay, so if I have a drone, a multispectral drone, how do I fly it, at which altitude and so on. And here comes a conflict, not a conflict, but what do you want to achieve? Something that is cost efficient or something that is very high precision. So here you have to make a compromise between time versus resolution. And this is defined mostly by at which height are you going to perform your flight mission. So we've done several tests. And of course, the lower you fly, the higher the resolution, but the more time consuming. So what we saw also that also due to some limitation, you cannot do some mission flight, automatic mission flight under 20 meters. That should be manual, depending on the drone, of course, and on the software. But drones cannot do a constant, maintain a constant altitude under 30 meters. So what we found was the best option in most cases is 30 meters. That was helpful for the farmers to know that. And okay, and the last part that's also for us it's quite relevant is for the in this pilot was the capacity building and a raising of awareness of the local stakeholders on these on the drone technologies. And this was a bit challenging because we have a problem, but I think it's not only in our region, but in most of Europe. It's the aging population of farmers with the obvious lack of knowledge regarding digital skills and use of technology. But nevertheless, we saw a very high interest in the technologies, but it has to be said that most of the interest was related for the spraying application. And unfortunately, in the Balearic Island, we have some very strict regulation regarding spraying application. We cannot perform any at all, not even for watering. So we were absolutely limited by that, and we were not able to test inside the spraying application. So this is a strong limitation for the agriculture, because this is the main point of interest for most of the farmers. And then one of the results we saw that the technology is still quite costly, but also not only in terms of equipment, but also in terms of skills and knowledge needed for that. So what we saw is that really farmers with a small scale, except if you have a very extensive crops, it's still not very suitable and cost effective for farmers, and it should be provided as a service either by a farmer cooperative or by companies. But still, at the same time, we've been talking with a lot of drone services companies, and they were telling us that it's not profitable for them. They earn way more money doing filming, advertising, monitoring a sports event, and so on. And the benefit in agriculture is still too low for them to be interesting to work with that. This is why this is also one of the recommendations to have support for application of drone technology in the agriculture. And that's it from my side. If you have any question, please let me know. Here you have my email address. Thank you very much.
So I'm Costa Davarakis, as Aris mentioned. I'm going to present two chapters of the livestock pilot. The first one will be describing an outline of the pilot itself, with the basic elements regarding expected results and outcomes. And then on the second chapter, we'll focus on a selection of added values that we deem as important for potential exploitation further beyond the project life. Right, so like this is the livestock pilot. While flora monitoring often focuses on stationary vegetation, mapping and biomass estimation, in animals monitoring, we have to use active methods like camera logging, bioacoustics, animal tagging to track something which is mobile, moving. Animal species tend to be difficult to spot. They are indeed elusive targets. So what we have in front of us is a livestock pilot that we try to configure to make it useful also for the end users. We had to put extra effort on that. So to extract farmers' needs, we organized an environment that took advice directly from the horse's mouth, if I may say so. So we organized an advisory group, an advisory board, which was supervised by SPADE itself, by Professor Bossis and his team there in Thessaloniki, the University of Thessaloniki. And we would be acting as the integrators, technology integrators, myself and my team from NST, and also, of course, members from the other partners that contributed from SPADE in the task, which is CERT, and it's also Fraunhofer, were very valuable in providing the AI-enhanced modules. Right, so when we started the use case organization structuring, the aspects addressed was discussed with the end user experts and professionals, and we thought that it would be important to have a rapid prototype, very fast in the project, where we would be tracking a first rudimentary sort of speech use case, and then we could build on that, have a baseline, and build on that, and make the use case more sophisticated, more intelligent as we go. So we structured 5 use cases grouped, and we managed to evaluate 3 out of them. Until now, we hope to be able to at least 1 more to evaluate it in the project lifecycle. The first one was detection and UAV guidance. This was a use case where we tried to deploy fusion of data channels. So we had, from one hand side, the UAVs, of course, obviously, that's the goal of the project, to experiment multi-purposes of UAVs in different domains. And the second data channel was coming directly from the animals. So we thought of utilizing wearable transceivers there to enhance the flight missions, the operation range for the UAVs. So that was quite interesting and successful, because it would be not only helpful for guiding the UAVs, but it is also an indication of basic well-being, behavior, or status of the animal and the flock itself. Now, the second use case, which is a more elaborate version of the first one, improved by introducing a direct access from the UAV itself to a prototype platform that was cloudified. And we were trying to organize within that platform digital twinning application assets, such as the animal behavior itself, the temperature of the animal, or that was not only for all the animals, that was only for the bell animal, which is the leader of the flock. That's what we try to implement in this second use case. The third one, which is still ongoing, in fact, introduced, in addition to that, aspects of virtual fencing and aspects of organizing data sets for organizing a more elaborate version of AI analytics, utilizing data sets for healthcare detection, health issues detection, well-being detection, and also the virtual fencing that you will be able to follow in a presentation after mine, after this session, in fact, by our sub-project, project that came out from SPADE Open Course, which is called Graceful. You will see there more details about the virtual fencing. What is interesting in that virtual fencing case is that we are now in the last mile of SPADE, testing swarming techniques for making little drones play the role of watchdogs that would go around the virtual fence and make sure that no animal, small animal, is trespassing. And finally, we have a use case that relates to detecting rich grazing landscapes. And we also have a use case that would be utilizing a very heavy and heavy-duty drone UAV to be able to relocate for care an ailing animal. But this is not going to happen within SPADE, at least, due to various reasons that you can imagine. Now, livestock pilot prototyping, we have developed a livestock pilot ecosystem that, apart from the UAVs, also introduces the concept of livestock technology solutions for livestock. The solutions can be grouped in 4 distinct areas or solutions. The first one is an application which is termed FlockSpy by Fraunhofer, and it is actually an edge computing environment that detects, counts animals, and then tracks them as they move around. It's a very interesting application. The second technology solution that we integrated is a set of wearable sensors that were mounted on the animals, as I mentioned earlier on. The third one is the open source cloud-based IoT platform, which is now we call it SPADE Livestock Platform, where we have various aspects of the grazing task being monitored, and the elements that come out from the drone itself, from the camera and telemetric data. In real time, you can view them on the cloud. And then we have a quite interesting, not very sophisticated in terms of technology solution, but comes very handy for farmers and novice UAV pilots, farmers and farming consultants, as we provided a robust and simple interface for commanding and controlling UAV devices that are quite complicated if you have analog interfaces. Running through the clock, as I see clock ticking, let me say that one of the interesting aspects is to monitor the environment on different types of UAVs. So we have tried to engage ourselves with commercial UAVs, a partner within the SPADE Livestock Pilot group purchased a Parrot Anafi USA UAV, which is quite interesting because it has the opportunity to utilize an SDK and access and interface the drone itself. That's the University of Thessaloniki who were kind enough to provide the specific commercial drone, but also we pay special credits to the SDU, who provided us with a small custom developed by them UAVs that we try to engage in our test cases. Now, concluding the first chapter, I may say that the pilot milestones were elaborated in such a way that we could look around and check if the goal, which is sheep and goats breeding and grazing, improved tasks there, could be assisted by the technology prototype that we were providing. And the technology prototype introduced not only the UAVs, but also the AI enhanced monitoring solutions that were developed. In the second chapter, I will try to make that more clear. But just to show you the analysis of the roadmap, it's a 4-year project. We started by rapid prototype just to showcase the concept and vision we had, and we tried. Now a set of trials were implemented, 5 in whole. Each one was very carefully structured to test the technology, to see feedbacks coming from the farming advisory group, and then to finally, for the last mile, to evaluate the complete set of use cases, at least the ones that we could make. So this is the first chapter we concluded. And Aris, if I may, I can move directly to the second one.
Yes, please, Kostas. Yes, go ahead.
With no further ado, let me highlight what we're going to see. The first thing is the custom UAV drone that was used. It's an environment developed by SDU They were able to mount Jetson Nano on board, which was very useful because on that machine, small equipment or device on board, airborne, we were able to upload the flock spy, and we could run some tests there with the UAV. This is the SDU small drone with Jetson on top. And we were able to run field trials with custom small UAV and Jetson Nano payload to track the flock, to make the first level of analytics. We were not able to run a real-time video on field laptop, not even in the cloud at that time, but we managed to, in real time, to see the output of the AI analytics and also some telemetry data coming from the drone itself. The challenges there were camera angles, the flock density, lighting, animal occlusion, and of course the clearance, the range of the UAV. Batteries were not sufficient to have more than 5 minutes flight with this type of UAV. This is the configuration again, and this is the output from the flock spy. You see the numbers coming out from the counting of sheep, and then you can also check there that the application on board bound the box around the animals that were spotted. So this is the opportunity for the tracking of the animal itself further on. Right, so this is the approach. Offline, after the flight, we were able to run the footage and see the bounding boxes on the footage that was maintained by the SDU drone provider. Now, takes from this trial allowed us to organize the second set of use cases, which was actually a trade-off between airborne edge computing and in-situ edge computing, which is again edge, but it's not airborne. So what we were trying to do there is, instead of having the AI tool executing the solutions and AI analytics on the Jetson, to have a field laptop, rather more powerful and also power-consuming device nearby in the field, where we could receive real-time video, and then, of course, cloudify the video to the SPADE livestock platform. Of course, we were also able to access higher resolution cameras, since the UAV used was a commercial one. It was actually the Parrot and Afi one. And due to the above, we opted to proceed with land edge computing, which enables real-time streaming of UAV cameras to the cloud. So that's the approach that we took, aligning now to the requirements coming from the advisory board. One of the requirements, one key issue, was to provide the piloting of the UAV service to be acceptable, adoptable, and accessible to the farmer itself and the farmer consultant. So we had to devise a user interface with a plug-and-play solution to lift the UAV from the land, from the field, and then to move it in a stepwise manner safely towards the flock. Navigating using small customizable steps, approaching the flock inconspicuously so that the animals are not get frightened. And finally, one of the issues was to store all the flight mission footage and data to a cloudified environment. This was implemented. This is the interface we provided to the farmers and the farmer consultants, so that they could take the control themselves of the small drone, take off automatically by button, land, and then move forward around, etc. You will see that in a minute in a small video we have. But this is the layout of the pilot. We have a farmer with a light laptop or a tablet, could be tablet. You also have, of course, the UAV and the camera. So this is the view from the UAV itself, and this is the farmer there. That's an edge laptop where now edge computing is being moved from the drone to the field. And then we have to the cloud, the complete environment where we can have the assets there being monitored by everyone that has access to the specific cloud platform. So this is the outline of the prototype. And there you can see a bit of the use case, how it was executed and how we proceeded. That's the UAV that is being commanded and controlled by the farmer himself. It could be any other approach, but this is just to show you that the interesting part is that the farmer itself, himself or herself, would be able to operate the small tablet with a small tablet, the approaching of the UAV to the flock. And this is the livestock platform prototype on the cloud. We have different assets, application assets that you can monitor, and different UAV devices that you can check. And going to the last mile, as I see time is very strict. The last mile for us is exploring some additional facilities. One of them would be virtual fencing that you will be able to follow in the next session. But the second one is the opportunity to evaluate whether we could have a set of healthcare issues being monitored. So we are trying to do that by developing our own models within the diaspora sub-project, SPADE sub-project, utilizing YOLO 26. So we are now, the group is now training the model with footage taken from their own farming settings, and they are now going into the approach where they have their vets, they have their scientists tagging the animals with potential health issues, and then they are trying to detect, associate the objects with a specific issue, and compute track metrics to identify differences between the normal behavior and the non-abnormal behavior. Finally, this is the final slide, just mentioning it to relieve everyone from livestock piloting. We have managed to evaluate 6 different formations: a small custom UAV, a commercial UAV, combined version of commercial and custom UAVs, and of course third-party commercial UAVs that were not totally part of the interface, like DJI. DJI is the brand that is being used by our subcontractor, by SPADE open call contractors, sub-projects. Swarming is the next big thing that we are doing, and we are testing that in June, where we will have small SDU drones acting as watchdogs, fencing around and watching trespassing events for the flock addressed. Thank you very much, everyone, for this opportunity, and back to you, Aris.
Hey, my name's Stefan Lloyd. I'm with Nebio. We're heading up the forestry pilot within SPADE. Today I've got 2 presentations for you. I'll go with the first one, which is autonomous below canopy drones for forest inventory and mapping. So the motivation here is that for sustainable forest management, we need to have continuous monitoring and inventory of the forests. Right now, with current technology, we can fairly easily do aerial scans where we basically just fly a drone above the forest and scan down onto the canopy, but really we only catch the canopy when we do that. So we miss a lot of the interesting stuff that happens inside the forest, like deadwood, vegetation, a lot of things that affect the ecosystem and biodiversity in the forest. And it also becomes difficult to extrapolate to tree species, size, and health. So what we wanted to do in this task was to deploy a LiDAR-enabled drone swarm below canopy. We want the swarm to autonomously navigate through the forest while assembling a point cloud map of the environment, also accurately tracking the drone locations, and that's using not using GNSS because it's often a GNSS-denied environment. And then also obviously avoiding obstacles. There's a lot of trunks, foliage, and branches that need to be avoided by the drones. And then the resulting data would be segmented and classified using our in-house AI algorithms. So methodology here, the platform was already presented by Thor a little bit. So we've got SPADE quadrotor drones that were built by SDU with onboard LiDAR and a Raspberry Pi 5 compute module. And we have a two-stage processing pipeline for this. There's one that's on board real time, a little less accurate, but is able to do a lot of things a little more efficiently and in real time. And then we have an offline post-mission pipeline for survey-grade accuracy and geolocation. The real-time pipeline uses FastLeo2 for LiDAR inertial odometry and live mapping. And then we have a modified fuel algorithm, which is a repository that does exploration and collision-free path planning. The offline point cloud assembly uses a custom GraphLab algorithm built on GTSAM, and it basically refines the Leo map using GNSS constraints when we do get them through the canopy, and also doing loop closures. AI analysis is done using ForestFormer 3D, which is a state-of-the-art AI point cloud segmentation algorithm for forestry developed by Nibio. The real-time navigation is done, well, I'll cover it now, but the challenge here is that GNSS is unreliable under canopy and the environment is dense with obstacles. And obviously all the autonomy and everything needs to run on board on the actual drone itself. So for localization and mapping, we use FastLeo2. Is the tightly coupled LiDAR initial odometry algorithm. Basically, it's taking subsequent LiDAR scans from the LiDAR sensor, doing a point cloud match, and then figuring out what the relative motion of the sensor had to be between those frames. But then on top of that, it's using the IMU, so taking inertial measurements, pre-creating and trying to get a good initial guess of where the sensor actually moved to, which speeds up the point cloud matching step. The output of this is a dense point cloud plus 6 DOF pose estimates at a fairly high rate. We feed this point cloud into an occupancy grid representation. So we basically voxelize it to a 10 centimeter resolution occupancy grid. And those are the orange boxes you see in the video that's playing on the right now. So that is where the obstacles are, and then we inflate that by the safety radius of the drone as it flies through the forest. Finally, we use a modified fuel algorithm. So fuel is an exploratory path planner. It's adapted here just to follow waypoints, but basically it generates smooth, dynamically feasible B-spline trajectories through free space, and it continuously replans as the map updates. And I had some videos here of the drone flying through the forest. Stopped, but you can kind of see the drone's view with the mapping of the forest and these collision boxes that it's avoiding, and that was all autonomous basically, so single drone autonomy, and the full stack runs on the Raspberry Pi 5. So we have the single drone autonomy, and the next step, which we're working on now, is to go from that single drone autonomy to swarm coordination. So the goal is to basically have a user interface where the user can input a polygonal area through a UI. You can see that on the side here. And then a central computer would divide up that polygon into a scanning grid depending on the number of drones and their launch positions. And you can see that down here in the lower right corner. And then each drone just basically receives a sequence of waypoints to follow, and it does its best to follow those waypoints while avoiding collisions with the environment. The drones communicate back to a centralized computer during this test with a telemetry link. So this is a low bandwidth radio telemetry link that carries critical mission data like the waypoints it needs to follow, pose feedback, and drone health. Heavier data like the actual LiDAR point clouds need to stay on the drones because we can't really use Wi-Fi over the distances that we need to in these tests. So basically, after the mission, the drones auto-connect on Wi-Fi to the central computer, sync their data, and then the maps are passed to the offline grassland pipeline for a final merging and geolocation. Here you can see a little video that we took. This is some tests with 3 drones swarm mapping a Norwegian forest. This was manually piloted because we don't have the swarm autonomous coordination just yet finished, but this was just to validate that the post-test stitching was working properly and that we were able to do this coordination. And you can see that here. So on the right, you have a stitch map from those tests where I've color-coded the point cloud based on the drone that actually took the data in question. And you can see it comes together quite nicely. So how that works, as mentioned, the real-time Leo map is quite good, actually, but it does drift over time. So basically, it's only ever taking relative measurements based on the previous frame. And it doesn't have any absolute measurements of where it is. It has no georeference. It has no GNSS input. So it can tend to drift over time. Maybe if you go 100 meters, it might get about a meter of air or like half a meter of air, which is not significant. But when you're looking at mapping a forest, you suddenly start getting duplicate trees and stuff like that if you go back to an area you've been to before. So we need to correct that. So we have an offline pipeline, uses GraphSlam refinement. So basically, we're using GTSAM, which is an open source GraphSlam repository. And it will warp the LiDAR inertial trajectory to match GNSS fixes when we get them. So if we get GNSS data, it will try to match that information. And then it will also detect and close loops if the drone revisits a location it's been to before. So as it's going through, if it sees that it's been to a location before, it tries to figure out where in that previous map it is now, again, by point cloud matching. And if it can't figure that out, then it adds that constraint to the map, and the whole trajectory up to that point will warp a little bit to accommodate that new piece of information. So you get a very optimal map at the end. Multi-drone merging works kind of in the same way. Basically, if one drone sees a part of the map that another drone has already mapped, it's able to try to figure out where in that previous map it is, and then add those same loop closure constraints, which allows the disparate maps to be stitched together seamlessly. And then the final step is to use AI segmentation. So these videos are not playing properly. Sorry about that. Not sure why. But basically, we have this AI algorithm that we've already developed on above canopy data that basically takes these point clouds and segments them into foliage, trunk, branches, and ground. And this is a very powerful tool for doing analysis of these point clouds afterwards. You can also do instance segmentation, where we're looking at figuring out what points belong to which individual trees. And you can imagine this is quite difficult once the trees start to overlap over each other. But these algorithms perform quite nicely, but we don't have big below canopy data sets that we can really train them on. So we're looking at addressing that within this open call as well. Within this task. And that will feed downstream per tree attributes like species, wood volume, health, etc. So for this task, at this point, we've got the GraphSlam pipeline, we've got the single drone autonomy, and we're just looking at wrapping up the swarm coordination and the final AI development, and then we'll be doing final integration testing over this summer. Right, so that was the first bit. I'll just move straight on to the second topic, if that's okay with everybody. So the second thing I want to talk about today is our work on Sky Planter, aerial reforestation with an ultralight seedling planting drone. So the The motivation here is that tree planting is a very labor-intensive and costly process with a lot of potential for automation. Current automation solutions are very large, they're expensive to transport, they cause significant soil damage, and as such, we see very low uptake. So almost all planting these days, especially in Nordic region, is done with manual planters, so people just walking around with a spade and planting trees. So we want to see if we could come up with a new solution to this, and our strategy was to develop a very lightweight seedling planting mechanism that we could attach to a custom drone by STU and then iterate and improve on that. And here you can see our first prototype on the right. So us at Nibio, we developed a custom lightweight planting mechanism. That's this thing on the bottom here, as well as the reloading mechanism on the top. It uses a double telescoping pneumatic design to reduce weight. It uses high pressure compressed air as a power source, and it plants in 3 motions, which I'll cover on the next slide. And in STU, as Thor already mentioned, developed a custom high-powered carrier drone. This has a custom design that allows this planting tube in the center here to go right through the very center of the drone, which is very important to let the seedlings drop through from the reloading mechanism into the planting mechanism, but also because there's very large reaction forces from the planting mechanism on the ground. And if those were not aligned with the center of gravity of the drone would just tip. But otherwise, it's a very high power, lightweight design and a completely novel spade innovation. So the planting mechanism works according to the image you see on the right. Basically, we have 3 concentric tubes that slide on each other in a double telescoping design on plastic sleeve bearings. So we've got an inner tube, which is rigidly attached to the drone. We have an outer tube on top of that, which carries the dibber, which is this triangular portion at the bottom of the mechanism, and a hatch. So this hatch can open up and release a tree. Then on the outside of the outer tube, we have a compression assembly. So that slides up and down on the outer tube. And that's this pincer mechanism here on the outside. And that's the role of that mechanism is to compress the soil around the tree. This is really important because without that compression, the tree will often die because it doesn't establish a good contact with the soil, and it can also topple over due to frost heave. Planting happens in 4 steps. So the drone will land on the target site. And then this planting dibber on the outer tube is explosively shot into the ground to create a hole in the ground and burying the hatch. Then the hatch is opened up with the side and releases a tree. And then finally, that whole hatch and dibber assembly is pulled up while the compression mechanism is pushed down, and that pushes the soil downwards and inwards around the tree, completing the plant. The key idea here is that all the loads from this planting runs through that very single carbon fiber tube, which makes sure that the loads are aligned with the center of gravity of the drone, but also significantly reduces weight. So carbon fiber tubes are very light, and we're talking about reducing weight of some of the existing mechanisms that might produce similar motions but have large steel hydraulics and external frames, going from what current mechanisms might have, which is like 600 kilos, 700 kilos upwards to a ton. For this, down to about 4 kilograms for our mechanism, which obviously is quite important if we're going to put it on a drone. The planting mechanism uses pneumatic air as a power source. So we chose to pursue pneumatics for this design because we needed explosive, very high power motions. And getting explosive motion from electrical power you either need to have heavy actuators or some kind of energy storage with springs, and both of these end up being very heavy. Meanwhile, compressed air is actually very high power, short duration actions with quite little mass. So even though the energy density of the storage might not be quite as efficient as, say, a LiPo battery, all the downstream elements become much lighter. And so the overall system becomes much lighter as well. We're also using a very high pressure storage tank. So we're actually using a carbon fiber paintball tank at 300 bar pressure, which is very high pressure. And then we do 2-stage regulation from 300 bar down to 7 bar. And because that compression ratio is so high, we actually get a lot of power out of this single 1.1 liter tank, enough power to plant 78 trees. And this is also, to our knowledge, one of the first uses of very high pressure compressed air in mobile robotics, and we think that that's an interesting application going into the future. The carrier drone is a custom quadrotor X configuration drone, 1.32 meter motor-to-motor diagonal distance. As I mentioned, the planting tube runs straight through the drone's center of mass, which is important to let the trees fall through, but also to align the reaction forces of the planting mechanism with the center of gravity of the drone, maximizing the planting force, but also preventing the drone from tipping. The body is made with carbon fiber sandwich plates, reloading mechanism on the top, and planting mechanism on the bottom. I won't go into the details of the drone itself because Thor already did that, but it's a pretty powerful, nice drone that Thor built, so kudos to him for that. Here I'll show you a video of the actual drone landing and planting. So you can see here it's going to do that planting sequence I described earlier. The shovel goes into the soil, opens a hatch, releases the tree, and then the compression mechanism descends a couple times to compress the soil around the tree. The seedlings themselves are quite well secured in the soil. The drone can plant multiple times in quick succession and reload. And this animation will show you some of the components of the design a little more clearly. So you can see here the planting motion again. Dibber goes into the soil, opens the hatch, goes back up, and then the compression mechanism compresses the soil around the tree. We'll show that one more time with the section cut, which shows it a little more clearly. The reloading mechanism basically just shifts the trees to the side, and then the tree drops into the central tube, and then it's planted in the exact same manner as before. Sky Planter is an ongoing piece of work. So we do have some ongoing challenges we're trying to explore. That's a bit loud, so let me introduce that. The main challenges are that the first design was not quite strong enough, so it was really only suitable for planting in soft soil types. And then the drone also could only land on nearly flat surfaces. So we're trying to address both those issues. Sky Planter 2.0 looks at doubling the planting and compression force to work on harder soil types. And we're also exploring reverse thrust to push the drone into the ground and then decouple planting force from vehicle weight, which is understandably quite important for aerial applications. And then we also have a self-leveling landing gear project that's ongoing as a SPADE open call, and it's actually going to be presented by Alexis a little later today, so stay tuned for that. But that's looking at using active braking to have self-leveling landing gear, which will allow this drone to land on uneven terrain, which is much more appropriate for, an arbitrary forest. Don't usually have flat terrain in forestry. So that's a really exciting piece of research, and I encourage you to stay tuned for that presentation later today.
I'm Efstathios Stavrakis. I'm one of the directors of Algolysis and a researcher in the team. We are an SME. We do applied AI and software engineering. We're an SME. Basically, I made this map because some people, you may not know exactly where Cyprus is. We are on the far southeast end of Europe. We're on the Greek part, which is a member of the EU. And we were founded in 2014. We do a lot of data-driven solutions, and we have many active funded R&D projects. So our focus areas are mainly distributed systems and applications, where we work on even basic research. There is also work happening in computer vision and graphics. And we do a lot of data engineering and analytics, and we have branched out into IoT systems and machine learning. So I'm going to show you a few examples of our previous work very quickly. My presentation is very visual, so I think it's going to be it's not going to be very tiring. And then I'm going to move on to Graceful to present you some of the work that we have done under the SPADE Open Call 2 project that we were awarded. So some of the stuff in the past, we've done simulations. So here there is a simulation in VR, and it's integrated with data communication in the cloud, with sensors. And then we also had another project where we did industrial object detection and recognition. There is a company, a manufacturer of toys in Cyprus, and we work with them under another European Union project, the SOP4CF Horizon project. And we built a very capable object detection and recognition model, and we presented that too. We also do a lot of data analytics, so we build platforms. We build a platform in the COVID time, and we have several others. We also do simulations. The simulation down here is an attempt to test our technology in distributed shared memory that we built, and we built a virtual environment to see whether this can be used in a VR and AR context. Another recent innovation that we came up with is the 3D motion search engine, where it allows content-based retrieval of 3D human motion, and it's quite new, that one. Other things that are more relevant to what you are doing, and we have been working for a few years in agri-tech, and we had a relatively large project in poultry egg production context. And we built both the hardware. This is our own hardware. We prototyped it, and we did all the casing and electronics and everything. Of course, the camera, this is an Intel camera, but the electronics of the sensors are ours. And we started from scratch, and we also built all the data pipeline for it. And also, of course, a farm management system to accompany and provide access to the farmers and mobile apps and so on and so forth. Now, other things we've done is, in that context, we've done some retrofitting, smart retrofitting of an egg grading machine. This is a dated grading machine where everything is manual. So we created a Raspberry Pi. We trained a model, a model that can run very, very sufficiently on the edge and can grade eggs very, very accurately. And we deployed that in the farm. This is a real farm. This is a business. It's not lab work. So we have a lot of experience. This is also the poultry farm where we have our sensors. We have wired 2 farms, and this is an ongoing effort. It's been for a couple of years now, and we collect a lot of data from there. And we observe not only visually, but audio and also environmental metrics. So we have a lot of experience with field deployments, where we are not just working in the lab. And then we started working in parallel in our project to build our distributed shared memory technology. This is a layer of algorithmic work for novel algorithms for distributed shared memory. Basically, it's a set of nodes where each node provides a space in memory, and this has also a communication medium on top of that, where the nodes can communicate wirelessly between themselves and exchange information. This is very powerful in context of drones, and we started prototyping devices and testing flights and intercommunication between drones. This is still ongoing work. It's been a few years, but we're getting there. So we basically, I think it's interesting to know, for you to know probably, that we also have three DJI enterprise vehicles which we used also in the Graceful project in SPADE. And I'm going to move on to that. So I've shown you some of the samples. We have many other projects that we've been working over the last decade. And we are trying now to overlap the technologies and try to build from TRL 4, 5, that most of these are, to a higher TRL and create products now. So we are at this phase. Of course, research is a major activity in the company, and we are very thankful to the SPADE project for selecting us, 1 out of 9 projects. We are really thankful for that. We were selected for building a virtual fencing system for grazing management, and also have some components for animal tracking and be able to do some land management. So I'm gonna show you a little bit the individual parts. So I have a lot of visuals. Basically, the idea is, the operational concept is that you define virtual fences around grazing areas, and then these virtual fences can be enforced digitally. So you don't have electrical fences and so on. We now have digital means to know where the animals are. Of course, there is passive tracking of animal collars that the SPADE project, the livestock pilot and Kostas has described earlier. And we also wanted to detect and monitor and record trespassing events and send some alerts and so on. And also another capability is to allow UAVs to survey fence boundaries on demand. So once you have an alert, you can request that a drone is dispatched to go and get visuals from the area. So this is the architecture. I think just for the sake of time, I'm not going to go into details because probably it's too complicated to describe. But basically, we were building this part here. So it's a field laptop where you collect the data from the UAV and the sensors, and then you have an interface to manage all these. And this information can be transmitted via an MQTT broker to the SPADE livestock platform or elsewhere. So what we've done is we created, the project basically integrates virtual fencing. It provides an interface for that. It integrates UAVs, the DJIs that we have, and also some wearable collars can be also integrated. And we actually have now a field laptop that we are using in the field. And it has some communication with the livestock platform, and this is ongoing work, of course. Although the project finished, we are still working on these items. So what we built is an application. It's a React application. It's a web-based application that runs on the laptop. It doesn't need a server or anything. So you can execute it locally on a field laptop. And this is important because we did not assume that there is cloud connectivity, which complicates things because you don't have the processing power or the storage capabilities and so on and so forth. And this has worked pretty well, actually. It's a very lightweight application, and you can define manually and semi-automatically. I'll show you a video instead of describing the features. So you have here your interface, and you can create virtual fences. You can go and manually, you see here the user this is a screencast. So basically the user defines virtual fences, and he can do certain operations on them to change them and so on. Modify, and it's also possible to annotate them and to give some thresholds. The thresholds are useful for doing the trespassing detection. So if an animal goes out more than 10 seconds and so on, it will issue an alert and so on and so forth. So this is one way to define fences, and we experimented with another way to kind of semi-automatically generate fences, because sometimes it may be tedious. So we thought maybe we segment the image and then let the user manipulate and choose which ones he would like to use. So you can kind of select what you want. It's a bit crowded, of course, there, but you don't have to use all of them. You can just choose and pick what you want and edit them. So this is the capability for virtual fencing. It's pretty straightforward, basically. We also integrated, one of the things we've done is with the DJI drones, now you can stream directly live feed from the drone into the field application. And of course, this means that you can timestamp it and tag it with events and store it and process it further. I'm going to show you a little bit of a video of what it looks like. These are pre-recorded videos, of course. What I'm showing here is that you can annotate them. So you can create certain types of annotations. So for instance, you're working with sheep. You can go and say, I have an incident of an animal being spotted. I'm gonna create an event. And the reason is that you can capture the video in the field, and then offline, you can go to a debriefing room and sit there and say, okay, what's happening here? I'm going to annotate the data. And this was a requirement because the SPADE platform, the SPADE project is looking for a way to collect data and then annotate them so as to be able to train models later on. This is what we understood. So this is quite useful. It's not real time. I mean, you can obviously annotate in real time, but it can be tedious because it's a live feed of video, so you may not have time. So you capture the video and then you do it offline, right? And you can play back and so on and so on. The other thing that we do is
please conclude as soon as possible because we passed the timeline. if you can conclude this.
Okay, so we have trespassing events. So you see a ship here, it will move around. I have videos for everything, so probably I don't have time. So when the animal tracked goes in and goes out, it will issue an alert. Maybe I show you just the alerts that are coming up and so on. There you go, you get it. And of course, this can be connected to other things. Now, another thing is there is mission planning. So the user can plan missions from the lab and then go and execute them. So you can select the waypoints that the drones will do. And it will, these are the waypoints that the drone will go on. Okay, the little numbers that are coming up. And you can automatically or semi-automatically have the virtual fence being traced. Okay. So I think that's it. And this is Nicolas, our engineer who is working on the project. This is the field laptop application. And then we also integrated the Fraunhofer animal detector. So you can, we can attach models to the live stream or the offline process. Actually, it works pretty fast and it's very stable. We noticed it's very stable. We get the counts here and so on, the frequency. But the counting and the tracking is really good. So thank you. I think I'll conclude here. Thank you for your time and really thank you for
thank you, Sirsa. Thank you very much. It was really interesting.
Mm-hmm.
We hope we had much more time.
Contact me. Sure. The details are on the slides. If you need any information or you want to follow up, I'm here. Yep. Thank you.
And of course, if anyone wants to has a question about our pilot, our open call use cases, you can send an email to us, and we will forward the question to the relevant part.
My name is Ali Kazemi. Thank you for the invitation. Today I'm going to talk about dipole drone image processing and analysis. We have been working on this project for 6 months, and the purpose of this challenge was that currently the drone image is a dominant sensor for precision agriculture, forestry management, and livestock monitoring. But raw images alone are not useful. Farmers and FMIS platforms need calibrated orthomosaics images, elevation models, and vegetation indices. Today's options are either desktop software that doesn't scale or closed commercial clouds with vendor lock-in. Dipole's goal is to deliver an open source AWS native API first platform that anyone in the space ecosystem can integrate. The core concept of this proposition is this. The operator uploads its collection of images from its drones to the pipeline, and it will automatically generate orthomedics images, DSMs, 3D point clouds, and vegetation indices from a single REST API or via the online platform. The whole procedure is end-to-end from the ingestion of the data to getting the results for calibration, SFM, orthomosaic, and so on. The platform is multi-tenant and secure via JWT implementation, RBAC, and also organization-level data isolation. The platform is FMIS ready, and any available FMIS in the business or open sources can be integrated with the platform. And the licensing is open source, so anyone in the GitLab of the SPADE can reach the developed repositories. The core architecture is three-layered, containing a front-end, back-end, and a gateway. All of these services are containerized and developed purely on AWS, but since they are containers, they can be moved to any other infrastructure as well. We use SQS-based development, so the user will be able to horizontally scale the whole platform. So the processing pipeline has 7 important steps from the time that the user wanted to start the processing of a database. From queuing and database to getting the results. And also the input will be sent automatically to FMIS platforms that have integrated their APIs. Our platform currently supports 6 different drones, and by the design pattern that we have used in the repositories, we are able to easily scale to any other drones as well. And finally, the results from the pipeline will include orthomosaic RGB or multi-spectral images, digital SFM model and hill shade, sparse and dense point clouds, and 3D mesh, and also the vegetation indices, including NDVI, NDRE, and GNDVI. Our platform is online, and you can access it for its platform or the APIs via the links that I have included, and visit the demo site via photogear.sensify.com. The highlights for this platform is that anyone can upload multi-parts of this file, so it's very fast. Its job lifecycle will give the operator to start, retry, or cancel a real-time stage tracking for both upload and also processing of a data set. And also the viewing of the mesh clouds are similar to what we have in open source applications for a better user experience. From the very first development of the project, we've validated the pipeline with automated test runs that run on every commits. Currently, the code base includes nearly 1,400 tests developed in unit tests, integration tests, load tests, and security tests. Also, the KPI dashboards are available via CloudWatch to track uptime, processing time, and security events. The platform is designed in a way that images will be from the different users can be tracked and processed at parallel. Thank you for your time. If you have any questions, I will be gladly to answer them.
Okay, so thank you everyone for inviting us and for the opportunity to talk today in this webinar and for the opportunity to work within SPADE, of course. This is I'm presenting our project, which is called Bloom, which is in case study 1, open field case study, and in the challenge of machine learning models for disease detection in Mediterranean crops. So I'm a machine vision engineer. I work at STAM, which is an Italian SME, works in consultancy and research and development for more than 20 years now. Our business unit is active in robotics, automation, and mechatronics, and of course also in machine learning and computer vision applications. So the rationale behind this project is to be able to detect occurring and very frequent diseases facing crops in the Mediterranean area, like olive trees and potato crops, provide a sustainable and scalable solution to do this detection using drone imagery. Performed and managed within the SPADE project, and enabling monitoring for farmers and end users of disease development and state through an infrastructure which is embedded in SPADE. So the objective of this project were, as we have said, to analyze these 2 cases of diseases which are in olive trees. So it's a tree orchard crop, and the potatoes, which are essentially plants. So we have developed, and we are still in the final stage of this project, machine learning models based on multispectral data obtained from DJI multispectral drone, and integrate this in a fast API that can be accessed by a web interface and also using a standalone application. So as I have anticipated, the data acquisition was managed with SPADE partner, and is basically drone imagery obtained from scans of olive use cases and potato use cases, so from these raw images, of course, one can obtain orthomosaic maps using DJI commercial software or using open source software like Open Drone Map that we have used. And this will result in the orthomosaic maps of both the RGB, multispectral bands, and also the digital elevation models. So let's get into details of both use cases. So as I have mentioned before, first one is the olive trees, and the disease, the particular disease of interest here is the repilo or olive leaf spots, which manifests, for example, in branches and leaves, as you can see in the upper right image. So with the agronomists and the SPADE partners, we have the three main levels of the disease were identified as severe infection, mild infection, and healthy tree. So there are several levels of approaches that we are following for tree detection, such as object detection, for example, using YOLO detector, using the RGB data. We can also use some prior knowledge of regions of interest encoded as a geo package, or also using 3D data, so basically segmenting the digital elevation model and digital terrain model to segment trees. So as you can see, as you can expect from the aerial images, the actual leaf spots are not visible in the image, but we are interested in modeling the response, the tree response, the vegetation response with the disease. So monitoring the multispectral data and then learning patterns where they correlate with the disease presence and severity. So the ground truth was provided by the SPADE partners and was performed on tree level. So the trees were labeled with one of the three possible labels. Then for each tree, a set of features were extracted based on multispectral bands. So the normalized bands and also the vegetation indices, which were referred to several times during this presentation, like NDVI, GNDVI, NDRE. And then a classifier is learned on top of these features to estimate so to map the features of a tree to a disease state. And several shallow classifiers were implemented and tested for this purpose. And then after this step, a subset of relevant features. So we calculate an exhaustive list of features, and then we select the ones which better explain the prediction and align better with the disease manifestation. During inference, we run the tree detection and olive tree detection, as I've mentioned before, and then we extract the features, the selected subset of features based on the training set, and estimate this disease state using the classifier. As for the potato use case, which is intrinsically different because we don't have plant detection in this case, So our aim is to identify the alternaria in potato crops, which is lesions, presents itself as lesions to the leaves. And again, in this case, we have markers which deliver ground truth information on regions or plants or set of plants which are either healthy or infected. These are the two levels that we are dealing with in this case. Labels are applied as geo-packaged polygons, so we draw polygons manually. It's a sort of manual annotation derived from the markers provided by the SPADE partners. Then we actually extract features from patches, so we patchify, in a sense, the orthomosaic maps and extract features from patches. For example, we relied on 50 per 50 centimeters patches, and essentially patches are assigned a ground. Each patch is assigned a ground truth label based on the overlap with the polygon ground truth. So similarly to the previous approach, we perform feature extraction and then feature selection to obtain the subset of features which better explain the disease state. So during inference, we run the patch-wise feature extraction and, of course, excluding the non-vegetation areas. And then, we run the classifier of the extracted features. And of course, in this case, the dataset balance is essential. We try to subsample classes in order to maintain the balance in the training set. As I said, this solution is implemented as a fast API web service, which is also accessible via a sample web application based on Gradio, and it allows for the uploading of orthomosaic maps of different bands. It performs the alignment in case the bands are not perfectly aligned. For example, this can be seen with RGB or with digital elevation models. And then it extracts features and provide the heat map or the prediction, color-coded mask of the predicted outcome. There is also a supporting application, Windows application, Python, but runs on Windows and Linux to interact with this library, basically. These are some preliminary results of the olive use case and potato use case on selected fields. But we are still finalizing the final pieces of this library. Thank you. Thank you for your attention and for this opportunity.
Thanks, everyone. I'm very happy to be here this morning for us in Canada to present what we've been doing in this project, where we design an ultralight brake-activated and self-leveling landing gear for the tree planting drone that was presented a bit earlier. I will be presenting the work that Isaac and John have been doing at the University of Sherbrooke in Quebec, Canada. So to give you a bit of the context, now Stefan presented about the drone. I'm gonna try not to repeat too much, but basically in this project there was a relatively large drone, around 30 kilograms, that needs to land repeatedly to plant trees. Obviously, when we are planting trees in forest environment, the ground is not perfectly flat or horizontal, and that's a challenge for drone landing. So our goal within this project was to develop the landing gear to allow the tree to land successfully and quickly onto forest ground. We did quite a bit of work in the field of landing drone in different locations. For the last few years, we've been using braking based strategy for designing our landing gears. We've been landing, as you can see on the picture, we've been landing the drone on some of our drone on fast-moving vehicle, like cars moving at 100 km per hour, on inclined rooftop, and on iceberg with spiny feet. I have a little video here. So you can see the landing at high speed. In all of these platforms, we've been using brakes within the landing gear. The nice thing with the brakes is it can dissipate kinetic energy without transmitting high load onto the drone structure. It's kind of a passive mechanism, so it's backdrivable and react instantly. It's usually lighter than motorized solution, mostly because you don't need to generate the power for braking and slowing down the drone. You can only dissipate the power. So in all our cases, that kind of solution allow us to simplify the control system and basically just control the drone to descend toward where we want to land and have the landing gear do the job. So we proposed to apply the same to the tree planting drone. So the idea is to descend the drone. We are targeting a descent speed that is relatively slow for us, but fast for most drone, of 0.5 meters per second. The legs are in a passive mode with very little friction at this point. Now we lower the drone while remaining relatively level. The leg can collapse under the weight of the drone. Once all of the legs are on the ground, we can apply the brake to slow down the descent and completely stop it. If we are not perfectly level, we can pulse the brake on enough to lower back to the desired height or adjust the attitude of the drone. So that's the general strategy that we're proposing. More specifically, you have the CAD drawings here, so you can see we have 4 legs that are actuated on the drone with our braking system. The leg consists of a square tube with a rack and pinion in there, so the inner tube can slide. There's a disc brake that is on each leg that can be where the braking force can be modulated by a servo motor, and we monitor the displacement with an optical encoder. All of this is pretty much all of the parts are 3D printed or laser cut, so it's really easy to manufacture. And the servo is a fast-acting servo, so we can react very quickly. That system, we had to integrate that system within the drone infrastructure. In gray here, on the left, we see what is already included on the drone, and on the right in light orange, we have what was added by us. So we have We have a central electronics controller that coordinate all of the legs together, get the information about the attitude of the drone and the desired state. Are we in the descent phase? Do we want the leg to lock? Do we want to adjust the attitude? And we communicate back to the drone different state about the working of the legs. Each leg has a small control circuit board that mostly do the high speed control loop to control the servo and read the position of the leg. So that's about it for the electronics. On the software side, we have a high-level control strategy that decide what to do with each leg. The command are sent to each of the leg control module, and the position of the position of the legs are then controlled. So I have a video here of a single leg being lowered at a control speed. So that's really nice to see that we can do that accurately and brake precisely. We see some. We made a mock-up. We don't have access to the full drone as part of our project. We're gonna now ship the leg to Stefan for integration. So we made a mock-up here. We see the foreleg being built and being displayed in a natural environment. We are in the final phase of integration right now to do like the full control and test the KPI. But we have we think we have a very nice solution where we can now support the weight of a heavy drone. Absorb the landing energy, adapt to different terrain, and do that relatively quickly so that we can take off again and plant other tree. As I said, we are in the final phase of our KPI validation. As part of this project, we will also provide smaller scaled down version for the LiDAR drone that were presented in the project and documenting all our design. We think the solution is quite innovative and novel in the field. We haven't seen things like that, so we are thinking about maybe publishing the result in the control strategy. We think that we can further reduce the weight of the landing gear. So that's pretty much always the case. The first time you design something, you find room for optimization. There is some interesting things on the material selection for the friction disc. Often for cars or mountain bike, you have steel is used, but that's not the best for a lightweight solution. So we have some interesting option that we have been investigating. And we think we can use the landing gear for many other applications also, including landing on moving platform, like for example a ship in rough sea. So that's what I had for you today.
Wonderful. So I will just start with a short introduction. I'm not going to take too much time because it's just a brief overview of the project and what we are trying to achieve through Icarus. And then Vasilis will take over and talk about more interesting things regarding the drone spraying applications that we have and the use case that we have in our project. So started on with the first, let's say, to say a little bit about the concept of Icarus and the vision. Basically, we see the project as a game changer in the use of drones. Basically, what the project was built upon is that we build upon the knowledge, the existing knowledge gaps that we have, different risks and barriers associated with the drone use in agriculture, but also in rural areas. And in order to tackle these challenges, basically the project developed a strategy to close these gaps and reduce the risks and scale up adoption. So we have started with the current state of the art. So the project is proposing an application-oriented approach in order to explore the multi-purpose application and the potential also of drones in agricultural production, in forestry, and in rural communities. So here we see 4 different, let's say, building blocks that they are the main components of the project. So we have, first of all, the research. So we have done a research on the drone innovation ecosystem in order to understand and exploit the possibilities to use drones as multi-purpose vehicles, to assess and optimize the drone-related technologies, and also analyze different standards and regulations and risks associated with the use of drones. The second part is to develop and demonstrate the different multiple innovative approaches for the application of drones in crop and livestock monitoring, in spraying, in forestry and biodiversity, and as well in rural logistics. And this is something we did in order to assess and reduce the risks that is actually coming up from the use and also from activities that we perform, just like we will describe later on with the spraying application. We also want to strengthen capacity. So basically, we developed a free online course. It's open access, education training, and also included value-added services in order to develop fundamental skills for the European stakeholders for the application of drone technologies. And finally, to build the European innovation ecosystem, to develop business and governance models, and also to scale up, let's say, increase the sustainability, performance, and competitiveness of the use of drones. If we move on to this graph, we can see here that we're basically what we have developed. So Icarus, we can see as the main, let's say, output of the project is the platform, the Icarus platform. So this is a web-based interactive platform in order to accelerate the use of drones for different sectoral and societal purposes. So here we can see the different components of the project. Basically, these are essential elements of the project, namely different work packages and work that we are completing. So we have the drone market landscape, which provides an inventory of the current drone market intelligence. And as we mentioned, so key actors, market needs, innovation, standards, regulations, and risks. We also have the drone data analytics library, where we have an open access repository for existing and emerging drone data analytics models and algorithms. We also have different, let's say, updates and highlights from the use cases and the open call trials, which is part of the project. And of course, we have performed a socioeconomic and environmental impact analysis. This is something that is currently, as we move towards the end of the project, we're finalizing these results. And we, as we mentioned earlier, we also have different business and governance models in order to empower stakeholders to explore the opportunities using drones. And finally, the Icarus Academy that I mentioned before, which is about capacity building, and it's providing different options to the stakeholders. Moving on to my last slide before Vasilis goes into more technical aspects. Here we can see the different use cases from Icarus. As I mentioned, the project is mostly adopting, let's say, an application-oriented approach to understand, to explore the potential of drones. So here we have basically two fundamental applications that they represent the eye in the sky. So we have monitoring applications like crop monitoring in Spain, livestock monitoring in France, and forestry and biodiversity monitoring in Lithuania. And we also have what we call hand in the sky applications for spraying and goods delivery. So the drone spraying application use case in Greece, and the rural logistics that's taking place between Greece and North Macedonia. We also had 20 actually different open calls, two different types, so the push and pull, in order to provide financial support to third parties, and also to harvest ideas, to get ideas from the stakeholders, and also to accelerate the let's say this network for the adoption of technologies that already exist. So this is a little bit about the project, and we can move on to Vasily for the next part about the drone spraying.
Yes, thank you very much, Katerina, for the introduction, and thank you also to Aris for having us in this wonderful event. So my name is Vasilis, and I'm going to go through our work on the drone spraying that we have completed during the last 3 years. We have produced some very nice results that we're going to go through. And overall, it's quite a unique use case because I believe it's the only topic covered today on drone spraying. And as you will see soon, it's quite a critical one. So what's the general objective of our use case? Back in the day when we were designing everything, there was this new technology that had already been introduced and a lot of people had already adopted it. But the thing is that very few people know how to actually use this technology properly, and even fewer know how to properly mitigate risks that exist in this, let's say, new type of application. So the use case fundamentally tries to assess this new technology, see whether it's feasible and whether it can actually operate and give benefits to the farmers. And at the same time, also compare it to the conventional standard, which is terrestrial sprayers. And as it's practically newly explored grounds, we're also trying to identify risks and at the same time come up with measures on how to properly eliminate them, if not even suppress them. So what are we trying to do here? We have practically adopted various experimental protocols that have been used in terrestrial spraying modeling for several decades now. And we have tried to readjust them slightly, but still stay within the safe boundaries to produce comparable and tangible research. And we try to study two phenomena. The first one is that as we drop plant protection products from the sky, we try to see what happens within the field and what happens outside the field. So it's two different systems that are obviously directly connected, but they are measured through different methodologies. So the first aspect of our use case is we try to model everything that happens during aerial spraying. Now, the second one, because we have the joy of having the Hellenic Crop Protection Association as a partner of our use case, we have also gone through various legislative, let's say, procedures to obtain experimental permits and conduct plant protection applications with drones with actual commercial products, which is going to be the second half of the presentation. So overall, this is the overview that we try to test this new technology. First, we try to model it, and then we try to see how well it performs on the field. The goal is to collect field-based evidence on this new technology, prove or disprove that it's safe or not. And overall, the idea is that we will try to push, and we still do that actively, we try to push towards a regulatory switch, because the greatest barrier that we have right now in the sector is that crop protection with drones is considered an aerial spraying, and aerial sprays are outright banned in most European member states. So this is the thing, that at least although research institutes are requested to provide data that prove that this new technology is safe, we're still in a very early stage, but this is something that currently is on the work. So next slide, please, Katerina. Yes, thank you very much. So very briefly, what's the theory behind drones and why this new technology is so popular with people, even when we are lacking the theoretical basis and evidence on their safe use? So first of all, it's a robotic platform. We can predetermine everything. We can create a flight path, and then the drone operates itself. This has numerous advantages on itself. First of all, the platform is far away from the user, so the user has minimum contact with the often hazardous agrochemicals. And the other one is that they can very easily access hard to traverse terrains like slopes, for example, which in conventional terrestrial machinery is probably the highest risk for operator health and generally the major source of injuries in agriculture when the terrestrial machineries just flip when they enter very steep terrain. Now, they are a flying platform. They eliminate soil compaction and they operate on LiPo batteries. So once a sustainable, renewable framework is established on a local level, they can eliminate fuel dependency, fossil fuel dependency. Now, at the same time, we're talking about a machine that usually weighs roughly 20 to 50 kilograms, depending on the model. This machine can roughly carry most of its payload, like 80% in water. So this is a very small tank compared to very large terrestrial sprays that can often carry 1 or 2 tons of water. So by default, UAV spraying is conducted as an ultra-low volume application, meaning that the final product is diluted in much smaller volume of water. So we end up with very highly targeted applications that can be enabled because drones have very accurate positioning systems. And this, as a, let's say, result, they also save a lot of water in crop protection applications. So this is the benefit. And now what's the shortcoming? The shortcoming is not operational, it's legislative. We are currently, as I mentioned, prohibited from using any aerial mean to drop plant protection products. We can't do so for fertilizers and water, but there's little to no benefit in doing so with such a small volume available. So overall, the legislative barriers currently what's prohibiting the faster adaptation, and a lot of people do not know of this. Drones, as I mentioned, are free to buy. You can buy them and drop water if you want, although there's no reason to do that. But a lot of people end up buying it without knowing that it is prohibited. And the other thing is that we are talking about crop protection applications, which is by default a very complicated and complex system. So a lot of people do not know what's optimal on conventional means, even more so in drone spraying, which we have another axis, another degree of liberty to move the aircraft around in 3 dimensions. So there is some theory as well on the operational aspects, that you have a very heavy machine, relatively heavy, but still heavy, that needs to remain airborne. So this creates a very strong downwash, and this downwash actually tries to push the droplets within the canopy and also creates a form of a barrier that prevents them from scattering around and going outside the targeted area. So next slide, please. Thank you very much. So I'm going to start to talk about the parameters that we try to model, because modeling actually comes from a series of sensitivity tests, and we try to see how different parameters interact with each other. So as I mentioned earlier, with drones, we have the liberty of moving freely on 3D space instead of a terrestrial grounded vehicle that can move on a 2D axis. So one of the benefits that is given to us now is that we can go on top of a row if we talk about a row crop like vineyards, or we can go between the row. And of course, this is optimally designed based on the width of the wingspan of the drone and the positioning of the nozzles overall. So this is the first parameter that we have to consider. Aside from positioning, which is again one parameter by itself, it's how far away we are from the canopy, because pneumatic spray nozzles actually operate on the form of a pyramid. So you also have to consider how this affects the final product, which is the spraying on the target. So next one, please. Yeah, I'm going to go a bit faster, sorry for this. So what happens from an engineering perspective when we have a liquid that cannot be compressed? Of course, when it exits the outlet of the system, it does so with greater pressure. So when we increase operational pressure, this actually creates smaller droplets that are more susceptible to be swept away on the wind, in contrast with heavier droplets that are, of course, more easy to go down. So next one, please. I will try to speed up a bit because I understand that we have very limited time. So we talked about the two aspects of the experiment. The first one is the modeling one in vineyards, which was identified very early on the project as the crop of interest because it's a 3D crop. It is quite very interesting to see what happens in the different layers of the canopy. And for that, we have adopted different ISO protocols to measure what's happening inside and what's happening outside. So if we go to the next slide, we will see the first of these protocols, protocol ISO 22522, which states what is the optimal sampling, let's say, methodology for such experiments and what are the parameters that we have decided on the experimental design, which is in our cases, altitude, flow rate, which under constant area, let's say, rate per application is translated as speed of application, and then the spraying position, whether it's on top of the row or between. So every yellow dot that you see here, if we move on the following slide, you can see that it is actually a water-sensitive paper here, yes, which is positioned in different altitudes, and the different altitudes actually they give us a better understanding of how well canopy coverage is achieved. If we move to the next one, please, you will see also an example of different samplers. Here you have it. And we also measure the position on the ground, which is, of course, something that we do not want when the target is canopy. So on the following one, this is what happens within the field. What happens outside the field, we have a different ISO 22866, which states how collectors should be positioned. And if you go on the next slide, we have some images as well. No, actually, we have the requirements, which I'm not going to go through now because of time limitations. But the idea is that here we do not spray with water. We spray with a color tracer, tartrazine, namely E102. And then everything is collected to the lab, and based on the concentration in different distances, we get estimations of how droplets move. So if you go through the next two slides, I think, yes, the next one is the equations. And the final one should be the result. So this is overall what the use case tries to create. We have completed already two peer review publications on what happens within the field, canopy graphs like that. And then we have another publication on drift curves, which is on the right. So I would like to ask now if we have enough time to go through for like 3 minutes probably to see the efficacy trials that we have conducted within the project, or we are like out of time already.
Yeah, we are behind the schedule, Vasilis. So if you can.
Okay. Yes. So maybe,
yeah,
maybe just a very brief 1 minute to go through the trials, because it would be nice to show them. So Katerina, if you can please go through the next slide, even after that, until we have the efficacy trials. Here, perfect. So the other half of the experiment is that aside from modeling, we have decided on some, let's say, crops of interest. So in collaboration with the company members of HCVA, we have obtained experimental permits because it's otherwise illegal to conduct spraying, even for research purposes, using actual plant protection products. And some of these cases are the maize herbicide that we did in Aliartos, an experimental farm of university, then rice in Halastra in the northern regions of Greece, and then again wheat in the central regions. And aside from that, it's in the following slides, but I'm afraid I will not reach there. We have also done a very interesting case on maize insecticide, because normally maize insecticide is performed when no terrestrial machineries, at least in the Balkans, are actually designed to go through the cornfields at that stage. So we do not talk about a comparable result, but rather a new opportunity that is generated by the drones. And then the final application that we did was a defoliant application on cotton, which again presented very nice results. If we go through just the final slide, because that's the take-home point I want to give you. So this is a very brief overview of the experiments, and we have the loudest. Yes, you can continue, Katerina, please. Show some images and conclude. Yes. Here are some images from the herbicide application, and yeah, one final slide on the rice, please. Here, that's the final slide. No, the one with the platform. Yes. Because that's a very interesting thing. Consider that in RISE, especially, it's a very popular thing and very popular technology to adopt because, as you can see here, in RISE, we have paddy fields. So paddy fields cannot be traversed with rubber wheels. They use these gear-like steel wheels on tractors that cannot enter the road. So instead of going through this whole process of carrying the tractor there and then dropping the tractor to operate, the rice growers are presented with the alternative of just having a drone to do everything that can be carried by a single car. So yeah, that's the thing. Overall, very comparable results to most of them. In herbicide and desiccant applications, drones have outperformed the conventional machineries. So if anyone would like to go through, yeah, unfortunately, we not go through the results. I took too much time in the beginning. More any question on specific results, I assume this publication will be open to everyone, but if any, let's say, questions arise about the results, we would be happy to reply via, I assume, email or any other form of communication. So thank you very much for that, and apologies for taking a bit of.
Okay, so Osborne, should we start with the first topic about? It's about DG Agri policy perspective on CAP, Green Deal, sustainability and digitalization, and how drone and data innovation can be integrated into policy tools and incentives.
Yeah, but do you want me to say something about that?
Well, you're moderating this session, right? For the policy. Mm-hmm.
Okay. Yeah, it was a lot of presentation about open access, open source, and using GitHub. I also checked with the document published by SDU. It was not. It was behind some wall, actually. So I just want to know from all participants: do we really want to have open access for publications and also for the open source? So how does it really act for the community, for the external beneficiaries?
Maybe I can start on that one.
Yeah.
Okay. Since I'm working on standardization. So basically, we have several parameters to take. First, parameters to take into account. First of all, we are dealing with ecosystems. Lots of things we put together. That's what we saw today. Okay. Secondly, there are information that we want to make available so that actually the ecosystem is up and running. Okay, so open source is one of the solutions. We saw the basics digital twin, how it is being used by Gradient, and also on top you have other open source things. Okay, and also mentioned a number of standards. In the previous talk, there was a presentation of 22866, which I was not familiar with, but of course it's actually the old standard, but we use them. Okay, so we have information and software which we want to make available, but we also have maybe IPR issues and protection issues, and I would say basically that we need help in terms of governance. Okay, and one of the example I want to mention, and I'm very much involved there, is cybersecurity. Okay, so we have started in the SPADE project thinking about the drone cybersecurity. Some other countries, in particular China, was also involved in the standards. And today we are progressing very slowly, but hopefully we'll speed up in the future. We are starting now standards on the cybersecurity of systems, okay, where we take into account not only the technical aspects, but also the human aspects, because in the ecosystem, many of us were doing things, while piloting drones, supervising whatever, things like that, okay? And this is the overall, let's say, vision that is important. And the Cybersecurity Resilience Act will tell us that if we have an incident, we need to react very diligently. And so we need to prepare ourselves to do it. And therefore, I would say a drone ecosystem to be used by agriculture has to be prepared from that. To me, it's going to be super important that we deal with that. Yeah.
So, yes. Thank you. I was not listening to the ANSI from Ulu presentation either. So, but how do you feel we can connect the policies from the European requirements, which Ulu has presented into a viable ecosystem for our platform? I think Bhavini mentioned the vicinity platform, but that was actually when we started 10 years ago with this platform. So it has evolved through various projects. So so how can we ensure, as you said, or validate that the requirements from the European directives will be validated by the standard, actually, by the open source? You mentioned, of course, a standard because you know we have this evaluation standards which you are the expert on. So can we see some kind of profile which a drone project can meet in order to be evaluated on level 1, 2, or 3?
I can also answer that. It depends on if others have some opinions. At standardization level, we invented the terms like, well, where you're using, okay, we didn't invent, okay, but we started to use the term trustworthiness. And you have actually a working group 13 in JTC1, which is focusing on trustworthiness and trying to come up with even ontology and guidance. Okay, so and in SC42 AI, they started a preliminary work item. I think it's led by Korea on trustworthiness fact labels. Okay, so and it raised lots of discussion. I want to split it into two parts. Okay, so first of all, what are the things that you want to trust? And this is, of course, by analyzing the system and by agreeing, yeah, this is important, so we need to have it. Okay, for instance, data quality would probably be very important. Okay, so and therefore you would probably put some emphasis on that. So once you have defined all the we call it the trustworthiness facts. Okay, so the things that might be important, then we will for sure come up with zillions of such facts. So we need to characterize them and to prioritize them, okay? And define, depending on the domain, a profile of trustworthiness. So maybe a list, maybe only at the end of the day, 3 or 4 facts that you want to try, okay? So there was an example, for instance, of ethics and of even addressing the gender issue. So those could be important or not, depending on the maturity of the system. And when they become important, you would like to have verification and certification on that. Okay. So the notion of a bias is very hot in standardization, okay, of AI. And today we cannot say that we can certify it, but maybe in the future we will have facilities, capabilities on that. So it's a moving target, but the thing that is not moving is that we can list those trustworthiness facts, but let's say verifying them, certifying them is a moving target depending on how we mature. Okay.
Yes. Yes, and we also see that when we are working with the new European acts, especially that on the Cyber Resilience Act, which is really complicated to find that solutions are.
Just for you to know, the Cyber Resilience Act is absolutely important. So, and it's good that the regulators thought about it because we are witnessing incidents. We have to react very quickly, very swiftly. But standardization is lagging. We do not have a standard on resilience and cybersecurity in SC27. we might have some thinking in JTC 13, Sense and Elect, because of the regulation. So it's time to catch up. People on engineering, they do work on resilience. There is a standard in SC7 on resilience called system resilience, but we have the phenomenon of silo. So people working on cyber security resilience, they are not aware of system resilience, or they are not taking into account. So we need to work together, and the policymakers will help. That's why standardization is so high in the agenda in EU, but also elsewhere, so that we start to break the silos, in particular when you have transversal concerns such as cybersecurity, protect privacy, ethics, transparency, all those characteristics that are in reality transversal.
Thank you. Thank you. So we maybe now next topic, so we will not delay the meeting too much. Iris?
Osborne, I would suggest let's also open the discussion also with our policy officers and policy-related stakeholders that are invited here. I would like to ask your opinion on what are your needs, what are your questions about the SPADE results or any other. So this is an open question for all of you. If anyone would like to let us know what we're missing or what, your opinion.
Maybe I can start with it if you want. Thank you very much for the question, but also for the opportunity to participate in this conference. My name is Miguel Fernandez. I work at the European Commission in DG Agri, in the unit A4, which is the unit dealing with data governance and digitalization. So maybe on, let's say, on the aspects that are very much, let's say, needed from the policy side. So, well, first of all, I think that that of course Horizon Europe projects such as SPADE are very valuable for EU policy making, and we count on your research, to support the policies and the various instruments, notably the CAP, the Common Agricultural Policy, but also Horizon Europe and others. So, for instance, I think SPADE is a very good example because, well, as we saw in the morning, you are not looking only at drones as a technology. We have seen presentations this morning related to drone usability, governance models, trustworthiness. I remember also AI, the link also with the data spaces, and even different discussions on the regulatory framework. So I think this is really important, to focus really on developing an ecosystem for drones and the related digital services. But maybe on the concrete, let's say, evidence, or use cases that could help us from the policy perspective, I will try to highlight some concrete examples. So I think first, of course, is the evidence that you are able to provide on the real impacts of drones. So which drone applications are mature, under which farm conditions, and with what benefits and costs. So I think this could be for sure one thing. Then second, and there has been already discussions on this, is a contribution on with regard to the regulatory and implementation, let's say, frictions. So where the operators may face difficulties, as we are discussing today. There is also the question of business models, and sustainable business models, and here lessons learned from also for a policy perspective. I think this is very important, to understand what makes these business models viable but also affordable for farmers, including small farms. And then, of course, the data dimension is also crucial. There has been a lot of discussions on standardization and interoperability, and I think recommendations here would be also very welcome, because these are key aspects, that allow us to understand what we need to connect drone data with other systems, no? So such as farm management systems, machinery data, advisory tools, and others. So this, I think, would be the main elements. But maybe I could also highlight two practical things. Let's say so. Maybe together with the technical deliverables, I think, at least in my experience, the policy briefs can be very useful as well, no? And especially when we receive them, let's say at the right moment, no? So when they can fit the relevant EU processes, and I'm thinking here CAP implementation, digital simplification, AI Act implementation, and others, no? And maybe the second aspect is of course the communication, no? Communication and connection with other, for instance, with other sister projects, as we saw today, where especially where synergies, no, can be created. I think this is also a crucial aspect for us to, well, not only to avoid the duplication, but also to make sure that the results of the project can connect with what is already happening at EU level. So I think this would be from my side. We can, of course, always ask for more, but I think this covers very well the main elements. Thank you.
Thank you, Miguel. We appreciate your feedback. Actually, we have on board also, our pilots, so we can about the lessons learned, we can have from first hand, some key outcomes from our use cases. So maybe we can discuss this right after we finish with this discussion. I see that Javier raised his hand, and Emmanuel Viscos as well. So I cannot see who raised his hand first. So
I think it was me, but I was just going to provide a slightly different vision because, well, my role is precisely on open source and data spaces, so I was trying to provide this vision as well. So I don't know if there is somebody who is willing to react to Miguel's speech directly. In that case, I can wait. Otherwise, I can start with this additional feedback I can provide from this point of view.
So Antonio speaking, I would like to react to what Miguel mentioned, that it would be a very good idea that the sister project get together and maybe produce policy briefs or such out of our experience, because the good thing about what we do is we can justify them through all our pilots, okay? So if we have like an executive vision of policies that we can provide to you, and behind having, of course, the use cases, the experience, return from experience, open calls or whatever that are, this could be helpful, okay? And of course, some of them will relate to what Javier would mention, I'm pretty sure, okay?
So if I can just jump before Javier, because he gave me the opportunity, thank you very much. I'm Emmanuel Mikosh from the European Landowners Organization. So we do represent landowners, farmers, foresters, in Europe. So it's a very broad network of people using drones in different situations. So I think also in regard to what Miguel said already and Antonio, it's great to have additional reports, analysis. Thank you also for all the previous presentations. It was really interesting to see, that we are moving, that there's plenty of things available already on the table. But please don't forget to involve, when you're doing something, the stakeholders. So people, on which land and forestry you're doing all the services, because they have also their experience, they have also their needs. They can also guide you in what is needed. So a lot was already mentioned, like data governance, quality of data, the need to aggregate them, the skills. I would like just to throw, in addition, the infrastructure and rural connectivity, which is also key when we're speaking about access to drones. Privacy, safety, of course, because that's the biggest issue, and I would say the biggest threats coming, I would say, or the fact how to address the use of drones. When you're speaking about being a landowner and giving access to your data. Training gaps, access to knowledge, also that's very important. And how can you use them in different weather conditions, and of course between forestry, livestock, vineyards, rice, that's already mentioned. There is plenty of potential, but this is just how to use it and how to optimize that use. So we are very keen to use it, to have access to that knowledge. This is just to be sure that there is enough finance and that we're involved from the early stage of each project to be sure that we are listened to. That's all. Thank you.
Thank you very much, Marlon. Okay, so related to the involvement of stakeholders, we've done a lot of work with trying to involve.
Javier mentioning something or not? Javier.
Yeah, I can go, but I guess we are kind of summarizing just Aristotelis.
Yes, it was just summarize about the stakeholders engagement in the project. So in each of our pilots, we try to engage stakeholders as much as possible. We've been tracking, their opinion. We've been following up with them in different events that we organized, and we try to. Also, just a note: if you remember the presentation for the livestock. It was based on the opinion of the stakeholders. Actually, we did some changes based on the stakeholders' opinion to the implementation of the pilot. So and the developments. So we agree with you. It's really valuable to hear the voice of the actual users of its product. And that was one thing. And also for the crop pilots. In Mallorca, we had some. It was something like lessons learned actually from about the use of drones. We had some implications there. The regulatory framework didn't let us do some trials because of the size of the drones. You cannot fly in Spain drones larger than 10 kilograms. The sprayer drone is prohibited for sure. So we did some events there and with the local stakeholders. Actually, Pierrick is here with us. He can provide some details because they've done a lot of work there with connecting with the local policy makers and the local government to raise these issues. And there were a lot of events where we collected input from the farmers there. So if you wish later on, I think because we're running out of time, I think we should move on with the next. Then if we have time, maybe Pierrick can give us some details about these activities for the COP.
Sure, we can do it later. I will be connected if you want to have a chat.
Thank you, Pierrick. But I would suggest because we're running out of time, let's hear Javier. Sorry for.
No problem. So I can try to make it brief. So, thank you for inviting me to this panel. And as anticipated, I can provide in my role as program manager in data spaces at the Eclipse Foundation, I can provide you with this vision of how can we help what you are doing in SPADE and on this topic with data spaces, because at the end of the day, we've seen during today several use cases, several presentations where we are trying to solve problems. Some of those problems are more simple, some others are complex, involving multiple stakeholders. But at the end of the day, we are facing this dilemma that we need to share data, but we need to keep data sovereignty, and we need to be careful and mindful what data are we sharing with whom and under which conditions. So if we are trying to solve an individual problem from an individual farmer, it is easy. But if we go levels of abstraction upper, if we are solving cooperative problems, we need to aggregate different farmers. If we are talking about machinery manufacturers or technical solution providers, we need to aggregate more data and share with more people. And in the most complex case, if we are involving authorities or regulators, we would need to anonymize and treat this data in a certain way. So as we saw as well in some presentations today, data spaces are here to help in this. So we can do this in a federated, trusted, and secure way. And just wanted to let you know that the way we are facing this at the Eclipse Foundation together with our members is trying to build data spaces on two main pillars. One pillar is standardization, and the other pillar is trying to foster adoption. And this is something we can do as the Eclipse Foundation. We are liaising with standard development organizations, and we are trying to position our technology and protocols and interoperability solutions so it can be reused. And this is what we are doing, for instance, at ISO IC level. It is just to be published ISO IC 2151, Concepts and Characteristics of Data Spaces Part 1. And you will see, once it is published, that beyond providing this vision of how to implement a stack of interoperability protocols for data spaces, you will see that there is an example reference of how the Eclipse technology can help you solve this problem. And we are working hard in order to make this happen. And just to convey this message that we need this digital sovereignty and data spaces in order to build the future of our applications. And the Green Deal, our environmental challenges require this high-level data sharing. So there is no way we would achieve and measure what we are supposed to reach in the short term by 2030 and 2050, unless we learn how to combine what you already master, which is data extraction and data gathering for agriculture, together with enhanced data sharing capabilities. So that's if I were to bottom line this, would be we need to work together in order to make this happen and enable unlocking the data sharing capabilities on top of the agricultural data. Thank you very much.
Thank you, Javier. Okay, so should we continue the discussion, adding Pierrick in the discussion about the lessons learned, what about the regulations and stuff? We have a lot of things to discuss, actually, because we also have a lot of work done by Oulu in SORA and aviation regulations and stuff. So I would like to ask, before moving on with Pierrick, if we have any questions about what was done in our work about all these, collecting all the regulations, in finding the gaps and all these.
So maybe if no one wants to add, maybe I could just, because I think this is a very important point. So I wanted just to say that yes, on the legislative framework, I think it can be an enabler of digitalization in agriculture, and well, there has been different regulations mentioned in the morning. We have, for instance, the example of the Data Act, no. And I think it's a good example to exemplify this. No, before the Data Act, farmers and other users, no, of connected products, often they did not have the clear legal rights to access the data generated by their equipment and they used. And now with these new legal rights, I think this is very relevant for agriculture, because they can help farmers to retain more control over the data generated at farm level, and also to create value out of it. But I think it was very interesting to hear in the morning that there are still we still see frictions, let's say, and I think it's also because a drone in agriculture is not just a drone. It's let's say an integrated service, no. And what I mean by this is that we have, of course, the sensors, the geolocation data. We have a cloud, AI, farm management platform, and even sometimes a connection with machinery or more increasingly linked to data spaces. No, so this is the reason why different regulations may apply, and which may lead to multiple questions. No, so, can I fly the drone? Can I process the imagery? Can I share the data? Or what happens if there is a cybersecurity incident? No, as Antonio was mentioning before. So I think from a policy perspective, this is probably one of the main challenges. I think the EU framework is increasingly complete or advancing, but farmers and SMEs may experience several, let's say, parallel compliance questions. So here, I think that something that could be, of course, very useful is to have a simple, let's say, operational pathway, for a farmer or a cooperative or even an agri-tech SME, in order to be able to see the interplay, on how these legislative pieces interlink and relate. So just wanted to complement on this. Thank you.
Thank you, Miguel. Antonio, you raised your hand.
Yeah, I just want to add, thank you for the summary. Operational pathway is the way to go. I want to add that in order to solve that, the drone is an ecosystem. You have other ecosystems. This one is probably that will be deployed very fast. It's already deployed. So we need in the ecosystem better coordination and governance. So both, okay? So that actually when we know that the service is provided such that the farmer can use it with a very simple operational pathway, then we have the market, okay? But behind the machinery of the ecosystem, policies, governance, coordination, using the data space, we should have exemplar solutions and maybe go into reusable stuff, maybe with open source and things like that. Of course, standards.
That's true.
Yeah, if I may comment, I'm not sure if Pierik is now. It looks like Pierik is here now, but you know, in many cases, you know, the issue is not perhaps with the drone regulations and regulations in civil aviation. It's you have so many related fields like some like a national sectors and some regulated by EU, and you have GDPR and public security and criminal law and liability issues and telecommunications, cybersecurity. So it's still kind of like an open question that how these different related fields, you know, like relate to the norms in civil aviation. And for example, we heard from Pierik that the farmers are very interested in aerial spraying of crop protection, and we heard same from the sister project. But this is not actually an issue with drone regulation. It's an issue with the directive on the sustainable use of pesticides. And there was actually in 2021-22 there was like a push to renew this directive that it will make some exemptions for drones, which are perhaps and obviously different kind of aerial spraying application than the traditional manned aircraft from very high up. With drones you can do it without very low altitude, and but this push to renew the legislation, it ran into some internal disagreements in the EU Parliament and it was buried. So for example, I think in the sister project they got like a special permit to do some testing, and I know in my home country in Finland, the Chemical Safety Bureau can give research institutions some like a permits to test with spraying application of plant protection pesticides. But of course that is not much help for the farmers at the current point. So there's so many related fields that need to see some, and it's like Antonio said that there might be still some siloing on the different fields. So this is something that should be addressed.
Thank you, Ansi. And I think now we make a good fit in the discussion, having the impacts in Mallorca, right? The discussions with the local stakeholders, Pierik.
Yes, exactly. The thing also, I think we are in a clear case where, from a technical point of view, we have a lot of things that are already solved or already available on the market, and it's more on the reality of the ground now. Who is going to use these technologies and solutions? And farmers, a lot of time they told me, "I'm a farmer. I'm not a technician. I'm not a pilot or a drone operator." So everyone has to have clear its responsibilities also, and it's what I was saying. So from all the discussion we had at local and regional level, it seems clear that farmers, except if they are the owners of a very large exploitation, they are not going to be the users of these technologies. So this should be especially we think a service to be provided by cooperative, because also this is also another aspect that I was talking, that even for service providers, drone service providers, agriculture is not very profitable. They have other type of activity that they can do on drones with drones that are more profitable. So this is something also to take in consideration. The other things that also mention and see that most of the burden from, let's say, from an administrative point of view, or the limitation are regarding more the agronomic aspect, so use of phytosanitary products and things like that. And right now, this is also another problem. The list of phytosanitary products that is allowed for testing, because at European level, it's still totally forbidden to do spraying application. But just for testing, for studies and trial, you can use in very specific condition some spraying application. But still, the list of products available for this type of trials is still very limited. And for instance, what we've seen at regional but also at national level in Spain is that one of the sector of agriculture that is mostly interested is the one of a vinery and here the problem is that the products available for vines, there's none. They cannot use it because there are none, or almost none, I think. Sorry, I think someone was going to say so. But anyway, so I think we have to regulate on different aspects, on the agronomic aspect, on the technological aspect, on the, of course, the data, open source aspect. Even though when we are talking with farmers, cooperatives, and so on, it's maybe bad to say that, but they don't really care about open access, about data sharing, they just want first something that works and they can use and works. And this is, for the moment, it's a bit still too complicated, too restricted from a legal point of view. They still need a lot of training in how to use and how to interpret, because a lot of time, if we're talking about, for instance, monitoring, it's very hard for them to understand the result they get. So a lot of training and raising awareness still is needed, but there is clear interest.
Actually, to my knowledge, the stakeholders, the farmers, really want to use these technologies, drone technologies, especially for practical things like spraying. So please keep in mind that in cases, there are many cases where after rain, heavy rain, for example, it's too muddy. If you need to go in and do some spraying, it's impossible. Then you might lose your crop actually due to that. If you need to spray with fungicide, let's say, and it's too late, then you need to wait for the soil to dry out. It might be too late. Then this is a really good, nice tool also for uneven terrains like what you presented, Pierrick. Even here in Greece, we have many cases where the terrain is so uneven that no machinery can go there, especially for olives. So this would be a really good technological solution for these farmers, and we know that the farmers are waiting for it because they want to use it. It will solve many of their issues. And we had this feedback, Pierrick, also in Mallorca when we did the event in Mallorca, right? So but the problem is that there are practical problems with the application, not only regulatory, but also practical. So far we don't know what product to use, what concentrations to use. So there's a lot of work need to be done in terms of research, because imagine that with the sprayers that we use so far, we use a lot of water volumes, large volumes, and we dissolve the products many times in this large volume. But now with the sprayers, we need to shrink the volume, because you cannot fly, you cannot have so much water. The tanks are very, very small compared to the traditional ones. Yeah, so that was my. I don't know if Vasilis Psiroukis is on board or in the panel, because he's done.
Had to go, but
okay,
I'm still around. Yeah, so I can say from our side that we have a lot of. There is a lot of let's say interest from the farmers to use the spraying drones, as Vasilis mentioned, especially in crops like rice, where it's very difficult to go into the field. But we have to mention here, I'm not sure if Vasilis mentioned in the presentation, that the results are actually different per crop. So that's very interesting, because it needs more investigation. So it's not the optimum, let's say, solution, the spraying drone for all the different types of crops. So that's different parameters, they have different results and impact. So yeah, I think it needs more investigation work.
Totally agree. Thank you, Katerina. Okay, then I think the only topic that we didn't touch is the open call about the innovation perspective and policy regulatory clarify need for scaling services. But I say it's already too late. I think we touched base to a lot of the running issues that we. So I would like to have an open invitation to each one of you. If you have any questions that you need, any information from our sister projects that you might want to acquire, please let us know. I'm not sure if anyone would like to add something to our discussion. But, I realize it's getting too late, so I suppose many of you need to switch to another meeting or. Okay, then I suppose we should conclude the session. Thank you
Before
very
we
much,
close
everyone.
the webinar, could we try to open the camera so we can take some picture of you for our dissemination and communication activities?
Yeah, of course.
Primoresa, could you help us to take some screenshot, Primoresa? Okay.
And Septian, I would also like to invite everyone to go through the virtual room. It's quite interesting. If we can also share again the link to the virtual room, because we have the posters from sister projects, from collaborating projects, a lot of information. So you can wander around this virtual room and navigate and see all the information we have there.
Yeah, just for information about the virtual exhibition room, it's going to be available until 19th of May 2026. So we still have at least for about a month to discover our project and also our sister project, as well as some policy relevant publication from DG Agri and also from Forum for Agri Association. So please go ahead, and yeah, we will going to share all the kita quiz as well to all the partners and to all the speakers before we publish it on our social media accounts. And yeah, thank you everyone. Have you already taken the picture from everyone? Then everyone already on? Okay, thank you. That's from. Okay, thank you, Marisa. So get back to you, Aris.
Okay. Well, I would like to thank everyone for your participation to our event. I hope you enjoyed it. I hope you got really good take-home messages. We're here for your questions, of course. And with this, I would like to conclude the event, and we'll stay in touch.
Thank you very much.
Thank you very much.
Thank you. Bye-bye.
Thank you.
Thank you, everyone. Thank you, the panelists and also
Bye.
presenters.
Thank you.
Bye.
Bye-bye.